Section 2.4. The structure of agents 53. Percepts to actions. The reflex agent brakes when it sees brake lights. A goal-based agent, in principle, could reason that if the car in front has its brake lights on, it will slow down. Given the way the world usually evolves, the only action that will achieve the goal of not hitting other cars is to brake. Although the goal-based agent appears less efficient, it is more flexible because the knowledge that supports its decisions is represented explicitly and can be modified. If it starts to rain, the agent can update its knowledge of how effectively its brakes will operate. This will automatically cause all of the relevant behaviors to be altered to suit the new conditions. For the reflex agent, on the other hand, we would have to rewrite many action rules. The goal-based agent's behavior can easily be changed to go to a different destination, simply by specifying that destination as the goal. The reflex agent's rules for when to turn and when to go straight will work only for a single destination. They must all be replaced to go somewhere new. 2.4.5 Utility-based agents. Goals alone are not enough to generate high-quality behavior in most environments. For example, many action sequences will get the taxi to its destination, thereby achieving the goal, but some are quicker, safer, more reliable, or cheaper than others. Goals just provide a crude binary distinction between happy and unhappy states. A more general performance measure should allow a comparison of different world states according to exactly how happy they would make the agent. Because happy does not sound very scientific, economists and computer scientists use the term utility instead. 6 Utility. We have already seen that a performance measure assigns a score to any given sequence of environment states, so it can easily distinguish between more and less desirable ways of utility function getting to the taxi's destination. An agent's utility function is essentially an internalization of the performance measure. If the internal utility function and the external performance measure are in agreement, then an agent that chooses actions to maximize its utility will be rational according to the external performance measure. Let us emphasize again that this is not the only way to be rational. We have already seen a rational agent program for the vacuum world, figure 2.8, that has no idea what its utility function is, but, like goal-based agents, a utility-based agent has many advantages in terms of flexibility and learning. Furthermore, in two kinds of cases, goals are inadequate but a utility-based agent can still make rational decisions. First, when there are conflicting goals, only some of which can be achieved, for example, speed and safety, the utility function specifies the appropriate trade-off. Second, when there are several goals that the agent can aim for, none of which can be achieved with certainty, utility provides a way in which the likelihood of success can be weighed against the importance of the goals. Partial observability and stochasticity are ubiquitous in the real world, and so, therefore, is decision-making under uncertainty. Technically speaking, a rational utility-based agent. Expected utility chooses the action that maximizes the expected utility of the action outcomes, that is, the utility the agent expects to derive, on average, given the probabilities and utilities of each. 6. The word utility here refers to the quality of being useful, not to the electric company or waterworks. 54 Chapter 2. Intelligent agents. Agent. Environment. Sensors. How happy I will be in such a state. State. How the world evolves. What my actions do. Utility. Actuators. What action I should do now. What it will be like if I do action A. What the world is like now. Figure 2.14. A model-based, utility-based agent. It uses a model of the world, along with a utility function that measures its preferences among states of the world. Then it chooses the action that leads to the best expected utility, where expected utility is computed by averaging over all possible outcome states, weighted by the probability of the outcome. Outcome. Appendix A defines expectation more precisely. In Chapter 16, we show that any rational agent must behave as if it possesses a utility function whose expected value it tries to maximize. An agent that possesses an explicit utility function can make rational decisions with a general-purpose algorithm that does not depend on the specific utility function being maximized. In this way, the global definition of rationality designating as rational those agent functions that have the highest performance is turned into a local constraint on rational agent designs that can be expressed in a simple program. The utility-based agent structure appears in Figure 2.14. Utility-based agent programs appear in Part 4, where we design decision-making agents that must handle the uncertainty inherent in stochastic or partially observable environments. At this point, the reader may be wondering, is it that simple? We just build agents that maximize expected utility, and we're done. It's true that such agents would be intelligent. But it's not simple. A utility-based agent has to model and keep track of its environment, tasks that have involved a great deal of research on perception, representation, reasoning, and learning. The results of this research fill many of the chapters of this book. Choosing the utility-maximizing course of action is also a difficult task, requiring ingenious algorithms that fill several more chapters. Even with these algorithms, perfect rationality is usually unachievable in practice because of computational complexity, as we noted in Chapter 1. 2.4.6 Learning agents. We have described agent programs with various methods for selecting actions. We have not, so far, explained how the agent programs come into being. In his famous early paper, Turing, 1950, considers the idea of actually programming his intelligent machines by hand. Section 2.4. The structure of agents 55. Performance standard. Agent. Environment. Sensors. Performance element. Changes. Knowledge learning goals. Problem generator. Feedback. Learning element. Critic. Actuators. Figure 2.15 A general learning agent. He estimates how much work this might take and concludes some more expeditious method seems desirable. The method he proposes is to build learning machines and then to teach them. In many areas of AI, this is now the preferred method for creating state-of-the-art systems. Learning has another advantage, as we noted earlier, it allows the agent to operate in initially unknown environments and to become more competent than its initial knowledge alone might allow. In this section, we briefly introduce the main ideas of learning agents. Throughout the book, we comment on opportunities and methods for learning in particular kinds of agents. Part B goes into much more depth on the learning algorithms themselves. A learning agent can be divided into 4 conceptual components, as shown in Fig Learning Element Year 2.15. The most important distinction is between the learning element, which is responsible for making improvements, and the performance element, which is responsible for performance element. Selecting external actions. The performance element is what we have previously considered to be the entire agent, it takes in percepts and decides on actions. The learning element uses critic feedback from the critic on how the agent is doing and determines how the performance element should be modified to do better in the future. The design of the learning element depends very much on the design of the performance element. When trying to design an agent that learns a certain capability, the first question is not how am I going to get it to learn this, but what kind of performance element will my agent need to do this once it has learned how. Given an agent design, learning mechanisms can be constructed to improve every part of the agent. The critic tells the learning element how well the agent is doing with respect to a fixed performance standard. The critic is necessary because the percepts themselves provide no indication of the agent's success. For example, a chess program could receive a percept indicating that it has checkmated its opponent, but it needs a performance standard to know that this is a good thing. The percept itself does not say so. It is important that the performance 56 Chapter 2. Intelligent agents. Standard be fixed. Conceptually, one should think of it as being outside the agent altogether because the agent must not modify it to fit its own behavior. The last component of the learning agent is the problem generator. It is responsible problem generator for suggesting actions that will lead to new and informative experiences. The point is that if the performance element had its way, it would keep doing the actions that are best, given what it knows. But if the agent is willing to explore a little and do some perhaps suboptimal actions in the short run, it might discover much better actions for the long run. The problem generator's job is to suggest these exploratory actions. This is what scientists do when they carry out experiments. Galileo did not think that dropping rocks from the top of a tower in Pisa was valuable in itself. He was not trying to break the rocks or to modify the brains of unfortunate passersby. His aim was to modify his own brain by identifying a better theory of the motion of objects. To make the overall design more concrete, let us return to the automated taxi example. The performance element consists of whatever collection of knowledge and procedures the taxi has for selecting its driving actions. The taxi goes out on the road and drives, using this performance element. The critic observes the world and passes information along to the learning element. For example, after the taxi makes a quick left turn across 3 lanes of traffic, the critic observes the shocking language used by other drivers. From this experience, the learning element is able to formulate a rule saying this was a bad action, and the performance element is modified by installation of the new rule. The problem generator might identify certain areas of behavior in need of improvement and suggest experiments, such as trying out the brakes on different road surfaces under different conditions. The learning element can make changes to any of the knowledge components shown in the agent diagrams, figures 2.9, 2.11, 2.13, and 2.14. The simplest cases involve learning directly from the percept sequence. Observation of pairs of successive states of the environment can allow the agent to learn how the world evolves, and observation of the results of its actions can allow the agent to learn what my actions do. For example, if the taxi exerts a certain braking pressure when driving on a wet road, then it will soon find out how much deceleration is actually achieved. Clearly, these two learning tasks are more difficult if the environment is only partially observable. The forms of learning in the preceding paragraph do not need to access the external performance standard in a sense. The standard is the universal one of making predictions that agree with experiment. The situation is slightly more complex for a utility-based agent that wishes to learn utility information. For example, suppose the taxi driving agent receives no tips from passengers who have been thoroughly shaken up during the trip. The external performance standard must inform the agent that the loss of tips is a negative contribution to its overall performance, then the agent might be able to learn that violent maneuvers do not contribute to its own utility. In a sense, the performance standard distinguishes part of the incoming percept as a reward, or penalty, that provides direct feedback on the quality of the agent's behavior. Hardwired performance standards such as pain and hunger in animals can be understood in this way. This issue is discussed further in Chapter 21. In summary, agents have a variety of components, and those components can be represented in many ways within the agent program, so there appears to be great variety among. Section 2.4. The structure of agents 57. Learning methods. There is, however, a single unifying theme. Learning in intelligent agents can be summarized as a process of modification of each component of the agent to bring the components into closer agreement with the available feedback information, thereby improving the overall performance of the agent. 2.4.7 How the components of agent programs work. We have described agent programs, in very high-level terms, as consisting of various components, whose function it is to answer questions such as, what is the world like now? What action should I do now? What do my actions do? The next question for a student of AI is, how on earth do these components work? It takes about 1,000 pages to begin to answer that question properly, but here we want to draw the reader's attention to some basic distinctions among the various ways that the components can represent the environment that the agent inhabits. Roughly speaking, we can place the representations along an axis of increasing complexity and expressive power: atomic, factored, and structured. To illustrate these ideas, it helps to consider a particular agent component, such as the one that deals with what my actions do. This component describes the changes that might occur in the environment as the result of taking an action, and figure 2.16 provides schematic depictions of how those transitions might be represented. BC. A. Atomic. B. Factored. B. Structured. BC. Figure 2.16 Three ways to represent states and the transitions between them. A. Atomic representation. A state, such as B or C, is a black box with no internal structure. B. Factored representation. A state consists of a vector of attribute values. Values can be Boolean, real valued, or one of a fixed set of symbols. C. Structured representation. A state includes objects, each of which may have attributes of its own as well as relationships to other objects. In an atomic representation, each state of the world is indivisible. It has no internal atomic representation structure. Consider the problem of finding a driving route from one end of a country to the other via some sequence of cities. We address this problem in figure 3.2 on page 68. For the purposes of solving this problem, it may suffice to reduce the state of world to just the name of the city. We are in a single atom of knowledge, a black box whose only discernible property is that of being identical to or different from another black box. The algorithms. 58 Chapter 2. Intelligent agents. Underlying search and game playing, chapters 3 to 5, hidden Markov models, chapter 15, and Markov decision processes, chapter 17, all work with atomic representations, or, at least, they treat representations as if they were atomic. Now consider a higher fidelity description for the same problem, where we need to be concerned with more than just atomic location in one city or another. We might need to pay attention to how much gas is in the tank, our current GPS coordinates, whether or not the oil warning light is working, how much spare change we have for toll crossings, what station is on the radio, and so on. A factored representation splits up each state into a fixed set of factored representation variables or attributes, each of which can have a value. While two different atomic states attribute value have nothing in common, they are just different black boxes to different factored states. can share some attributes, such as being at some particular GPS location, and not others, such as having lots of gas or having no gas. This makes it much easier to work out how to turn one state into another. With factored representations, we can also represent uncertainty. For example, ignorance about the amount of gas in the tank can be represented by leaving that attribute blank. Many important areas of AI are based on factored representations, including constraint satisfaction algorithms, Chapter 6, propositional logic, Chapter 7, planning, Chapters 10 and 11, Bayesian networks, Chapters 13 to 16, and the machine learning algorithms in Chapters 18, 20, and 21. For many purposes, we need to understand the world as having things in it that are related to each other, not just variables with values. For example, we might notice that a large truck ahead of us is reversing into the driveway of a dairy farm, but a cow has got loose and is blocking the truck's path. A factored representation is unlikely to be pre-equipped with the attribute truck ahead backing into dairy farm driveway blocked by loose cow with value true or false. Instead, we would need a structured representation, in which OB structured representation objects such as cows and trucks and their various and varying relationships can be described explicitly. See Figure 2.16, c. Structured representations underlie relational databases and first-order logic, Chapters 8, 9, and 12, first-order probability models, Chapter 14, knowledge-based learning, Chapter 19, and much of natural language understanding, Chapters 22 and 23. In fact, almost everything that humans express in natural language concerns objects and their relationships. As we mentioned earlier, the axis along which atomic, factored, and structured expressiveness annotations lie is the axis of increasing expressiveness. Roughly speaking, a more expressive representation can capture, at least as concisely, everything a less expressive one can capture, plus some more. Often, the more expressive language is much more concise. For example, the rules of chess can be written in a page or two of a structured representation language such as first-order logic, but require thousands of pages when written in a factored representation language such as propositional logic. On the other hand, reasoning and learning become more complex as the expressive power of the representation increases. To gain the benefits of expressive representations while avoiding their drawbacks, intelligent systems for the real world may need to operate at all points along the axis simultaneously. Section 2.5. Summary 59. 2.5 Summary. This chapter has been something of a whirlwind tour of AI, which we have conceived of as the science of agent design. The major points to recall are as follows. An agent is something that perceives and acts in an environment. The agent function for an agent specifies the action taken by the agent in response to any percept sequence. The performance measure evaluates the behavior of the agent in an environment. A rational agent acts so as to maximize the expected value of the performance measure, given the percept sequence it has seen so far. A task environment specification includes the performance measure, the external environment, the actuators, and the sensors. In designing an agent, the first step must always be to specify the task environment as fully as possible. Task environments vary along several significant dimensions. They can be fully or partially observable, single agent or multi-agent, deterministic or stochastic, episodic or sequential, static or dynamic, discrete or continuous, and known or unknown. The agent program implements the agent function. There exists a variety of basic agent program designs reflecting the kind of information made explicit and used in the decision process. The designs vary in efficiency, compactness, and flexibility. The appropriate design of the agent program depends on the nature of the environment. Simple reflex agents respond directly to percepts, whereas model-based reflex agents maintain internal state to track aspects of the world that are not evident in the current percept. Goal-based agents act to achieve their goals, and utility-based agents try to maximize their own expected happiness. All agents can improve their performance through learning. Bibliographical and historical notes. The central role of action in intelligence. The notion of practical reasoning goes back at least as far as Aristotle's Nicomachean Ethics. Practical reasoning was also the subject of McCarthy's, 1958, influential paper Programs with Common Sense. The fields of robotics and control theory are, by their very nature, concerned principally with physical agents. The controller concept of a controller in control theory is identical to that of an agent in AI. Perhaps surprisingly, AI has concentrated for most of its history on isolated components of agents, question-answering systems, theorem provers, vision systems, and so on rather than on whole agents. The discussion of agents in the text by Genesirith and Nilsson, 1987, was an influential exception. The whole agent view is now widely accepted and is a central theme in recent texts. Poole et al., 1998, Nilsson, 1998, Padgham and Wienikov, 2004, Jones, 2007. Chapter 1 traced the roots of the concept of rationality in philosophy and economics. In AI, the concept was a peripheral interest until the mid-1980s, when it began to suffuse many. 60 Chapter 2. Intelligent Agents. Discussions about the proper technical foundations of the field. A paper by John Doyle, 1983, predicted that rational agent design would come to be seen as the core mission of AI, while other popular topics would spin off to form new disciplines. Careful attention to the properties of the environment and their consequences for rational agent design is most apparent in the control theory tradition. For example, Classical Control Systems, Dorff and Bishop, 2004, Kirk, 2004, Handel Fully Observable, Deterministic Environments, Stochastic Optimal Control, Kumar and Varaya, 1986, Vertakas and Shreve, 2007, Handel's Partially Observable, Stochastic Environments, and Hybrid Control, Hansinger and Sastari, 1998, Cassandras and Lideros, 2006. Deals with environments containing both discrete and continuous elements. The distinction between fully and partially observable environments is also central in the dynamic programming literature developed in the field of operations research, Puterman, 1994, which we discuss in Chapter 17. Reflex agents were the primary model for psychological behaviorists such as Skinner, 1953, who attempted to reduce the psychology of organisms strictly to input/output or stimulus/response mappings. The advance from behaviorism to functionalism in psychology, which was at least partly driven by the application of the computer metaphor to agents, Putnam, 1960, Lewis, 1966, introduced the internal state of the agent into the picture. Most work in AI views the idea of pure reflex agents with state as too simple to provide much leverage, but work by Rosenshine, 1985, and Brooks, 1986, questioned this assumption, see Chapter 25. In recent years, a great deal of work has gone into finding efficient algorithms for keeping track of complex environments, Hampshire et al., 1992, Simon, 2006. The remote agent program, described on page 28, that controlled the Deep Space One spacecraft is a particularly impressive example. Musitola et al., 1998, Johnson et al., 2000. Goal-based agents are presupposed in everything from Aristotle's view of practical REA. Soning to McCarthy's early papers on logical AI. Shaky the Robot, Fikes and Nilsson, 1971, Nilsson, 1984, was the first robotic embodiment of a logical, goal-based agent. A full logical analysis of goal-based agents appeared in Genesirith and Nilsson, 1987, and a goal-based programming methodology called agent-oriented programming was developed by Shaham, 1993. The agent-based approach is now extremely popular in software engineering, Chiancarini and Wooldridge, 2001. It has also infiltrated the area of operating systems, where autonomic computing refers to computer systems and networks that monitor and can autonomic computing trawl themselves with the perceive, act loop and machine learning methods, Kephart and Chess, 2003. Noting that a collection of agent programs designed to work well together in a true multi-agent environment necessarily exhibits modularity. The programs share no internal state and communicate with each other only through the environment. It is common within the field of multi-agent systems to design the agent program of a single agent as a collection of multi-agent systems autonomous sub-agents. In some cases, one can even prove that the resulting system gives the same optimal solutions as a monolithic design. The goal-based view of agents also dominates the cognitive psychology tradition in the area of problem solving, beginning with the enormously influential Human Problem Solving, Newell and Simon, 1972, and running through all of Newell's later work, Newell, 1990. Goals, further analyzed as desires, general, and intentions, currently pursued, are central to the theory of agents developed by Bradman, 1987. This theory has been influential both in Exercises 61. Natural Language Understanding and Multi-Agent Systems. Horvitz et al., 1988, specifically suggests the use of rationality conceived as the maximization of expected utility as a basis for AI. The text by Pearl, 1988, was the first in AI to cover probability and utility theory in depth. Its exposition of practical methods for reasoning and decision-making under uncertainty was probably the single biggest factor in the rapid shift towards utility-based agents in the 1990s. See Part 4. The general design for learning agents portrayed in Figure 2.15 is classic in the machine learning literature. Buchanan et al., 1978, Mitchell, 1997. Examples of the design, as embodied in programs, go back at least as far as Arthur Samuel's, 1959, 1967, learning program for playing checkers. Learning agents are discussed in depth in Part V. Interest in agents and in agent design has risen rapidly in recent years, partly because of the growth of the internet and the perceived need for automated and mobile software, et Sioni. And Weld, 1994. Relevant papers are collected in Readings in Agents, Hoons and Singh, 1998, and Foundations of Rational Agency, Wooldridge and Rao, 1999. Texts on multi-agent systems usually provide a good introduction to many aspects of agent design. Weiss, 2000A, Wooldridge, 2002. Several conference series devoted to agents began in the 1990s, including the International Workshop on Agent Theories, Architectures, and Languages, et al., the International Conference on Autonomous Agents, and the International Conference on Multi-Agent Systems, ICMAS. In 2002, these three merged to form the International Joint Conference on Autonomous Agents and Multi-Agent Systems, AMAS. The journal Autonomous Agents and Multi-Agent Systems was founded in 1998. Finally, dung beetle ecology, Hansky and Camberford, 1991, provides a wealth of interesting information on the behavior of dung beetles. YouTube features inspiring video recordings of their activities. Exercises. 2.1 Suppose that the performance measure is concerned with just the first t-time steps of the environment and ignores everything thereafter. Show that a rational agent's action may depend not just on the state of the environment but also on the time step it has reached. 2.2 Let us examine the rationality of various vacuum cleaner agent functions. A. Show that the simple vacuum cleaner agent function described in Figure 2.3 is indeed rational under the assumptions listed on page 38. B. Describe a rational agent function for the case in which each movement costs 1 point. Does the corresponding agent program require internal state? C. Discuss possible agent designs for the cases in which clean squares can become dirty and the geography of the environment is unknown. Does it make sense for the agent to learn from its experience in these cases? If so, what should it learn? If not, why not? 2.3 For each of the following assertions, say whether it is true or false and support your answer with examples or counterexamples where appropriate. A. An agent that senses only partial information about the state cannot be perfectly rational. 62 Chapter 2. Intelligent agents. B. There exist task environments in which no pure reflex agent can behave rationally. C. There exists a task environment in which every agent is rational. D. The input to an agent program is the same as the input to the agent function. E. Every agent function is implementable by some program/machine combination. F. Suppose an agent selects its action uniformly at random from the set of possible actions. There exists a deterministic task environment in which this agent is rational. G. It is possible for a given agent to be perfectly rational in two distinct task environments. H. Every agent is rational in an unobservable environment. I. A perfectly rational poker-playing agent never loses. 2.4 For each of the following activities, give a piece description of the task environment and characterize it in terms of the properties listed in section 2.3.2. Playing soccer. Exploring the subsurface oceans of Titan. Shopping for used AI books on the internet. Playing a tennis match. Practicing tennis against a wall. Performing a high jump. Knitting a sweater. Bidding on an item at an auction. 2.5 Define in your own words the following terms: agent, agent function, agent program, rationality, autonomy, reflex agent, model-based agent, goal-based agent, utility-based agent, learning agent. 2.6 This exercise explores the differences between agent functions and agent programs. A. Can there be more than one agent program that implements a given agent function? Give an example, or show why one is not possible. B. Are there agent functions that cannot be implemented by any agent program? C. Given a fixed machine architecture, does each agent program implement exactly one agent function? D. Given an architecture with n bits of storage, how many different possible agent programs are there? E. Suppose we keep the agent program fixed but speed up the machine by a factor of 2. Does that change the agent function? 2.7 Write pseudocode agent programs for the goal-based and utility-based agents. The following exercises all concern the implementation of environments and agents for the vacuum cleaner world. Exercises 63. 2.8 Implement a performance measuring environment simulator for the vacuum cleaner world depicted in Figure 2.2 and specified on page 38. Your implementation should be modular so that the sensors, actuators, and environment characteristics, size, shape, dirt placement, etc., can be changed easily. Note, for some choices of programming language and operating system there are already implementations in the online code repository. 2.9 Implement a simple reflex agent for the vacuum environment in exercise 2.8. Run the environment with this agent for all possible initial dirt configurations and agent locations. Record the performance score for each configuration and the overall average score. 2.10 Consider a modified version of the vacuum environment in exercise 2.8, in which the agent is penalized 1 point for each movement. A. Can a simple reflex agent be perfectly rational for this environment? Explain. B. What about a reflex agent with state? Design such an agent. C. How do your answers to A and B change if the agent's percepts give it the clean/dirty status of every square in the environment? 2.11 Consider a modified version of the vacuum environment in exercise 2.8, in which the geography of the environment, its extent, boundaries, and obstacles is unknown, as is the initial dirt configuration. The agent can go up and down as well as left and right. A. Can a simple reflex agent be perfectly rational for this environment? Explain. B. Can a simple reflex agent with a randomized agent function outperform a simple reflex agent? Design such an agent and measure its performance on several environments. C. Can you design an environment in which your randomized agent will perform poorly? Show your results. D. Can a reflex agent with state outperform a simple reflex agent? Design such an agent and measure its performance on several environments. Can you design a rational agent of this type? 2.12 Repeat exercise 2.11 for the case in which the location sensor is replaced with a bump sensor that detects the agent's attempts to move into an obstacle or to cross the boundaries of the environment. Suppose the bump sensor stops working, how should the agent behave? 2.13 The vacuum environments in the preceding exercises have all been deterministic. Discuss possible agent programs for each of the following stochastic versions. A. Murphy's Law, 25% of the time, the suck action fails to clean the floor if it is dirty and deposits dirt onto the floor if the floor is clean. How is your agent program affected if the dirt sensor gives the wrong answer 10% of the time? B. Small children, at each time step, each clean square has a 10% chance of becoming dirty. Can you come up with a rational agent design for this case? 3. Solving problems by searching, in which we see how an agent can find a sequence of actions that achieves its goals when no single action will do. The simplest agents discussed in Chapter 2 were the reflex agents, which base their actions on a direct mapping from states to actions. Such agents cannot operate well in environments for which this mapping would be too large to store and would take too long to learn. Goal-based agents, on the other hand, consider future actions and the desirability of their outcomes. This chapter describes one kind of goal-based agent called a problem-solving agent. Problem-solving agents use atomic representations, as described in section 2.4.7, that is, states of the world are considered as wholes, with no internal structure visible to the problem-solving algorithms. Goal-based agents that use more advanced factored or structured representations are usually called planning agents and are discussed in chapters 7 and 10. Our discussion of problem-solving begins with precise definitions of problems and their solutions and give several examples to illustrate these definitions. We then describe several general-purpose search algorithms that can be used to solve these problems. We will see several uninformed search algorithms that are given no information about the problem other than its definition. Although some of these algorithms can solve any solvable problem, none of them can do so efficiently. Informed search algorithms, on the other hand, can do quite well given some guidance on where to look for solutions. In this chapter, we limit ourselves to the simplest kind of task environment, for which the solution to a problem is always a fixed sequence of actions. The more general case where the agent's future actions may vary depending on future percepts is handled in Chapter 4. This chapter uses the concepts of asymptotic complexity, that is, O, notation, and NP completeness. Readers unfamiliar with these concepts should consult Appendix A. 3.1 Problem-solving agents. Intelligent agents are supposed to maximize their performance measure. As we mentioned in Chapter 2, achieving this is sometimes simplified if the agent can adopt a goal and aim at satisfying it. Let us first look at why and how an agent might do this. 64. Section 3.1. Problem-solving agent 65. Imagine an agent in the city of Arad, Romania, enjoying a touring holiday. The agent's performance measure contains many factors. It wants to improve its suntan, improve its Romanian, take in the sights, enjoy the nightlife, such as it is, avoid hangovers, and so on. The decision problem is a complex one involving many trade-offs and careful reading of guidebooks. Now, suppose the agent has a non-refundable ticket to fly out of Bucharest the following day. In that case, it makes sense for the agent to adopt the goal of getting to Bucharest. Courses of action that don't reach Bucharest on time can be rejected without further consideration, and the agent's decision problem is greatly simplified. Goals help organize behavior by limiting the objectives that the agent is trying to achieve and hence the actions it needs. Goal formulation to consider. Goal formulation, based on the current situation and the agent's performance measure, is the first step in problem solving. We will consider a goal to be a set of world states, exactly those states in which the goal is satisfied. The agent's task is to find out how to act, now and in the future, so that it reaches a goal state. Before it can do this, it needs to decide, or we need to decide on its behalf, what sorts of actions and states it should consider. If it were to consider actions at the level of move the left foot forward an inch or turn the steering wheel 1 degree left, the agent would probably never find its way out of the parking lot, let alone to Bucharest, because at that level of detail there is too much uncertainty in the world and there would be too many steps in a solution. Problem formulation is the process of deciding what actions problem formulation and states to consider, given a goal. We discuss this process in more detail later. For now, let us assume that the agent will consider actions at the level of driving from one major town to another. Each state therefore corresponds to being in a particular town. Our agent has now adopted the goal of driving to Bucharest and is considering where to go from Arad. 3 roads lead out of Arad, one towards Sibiu, one to Timișoara, and one to Zarind. None of these achieves the goal, so unless the agent is familiar with the geography of Romania, it will not know which road to follow. Point 1. In other words, the agent will not know which of its possible actions is best, because it does not yet know enough about the state that results from taking each action. If the agent has no additional information, i.e., if the environment is unknown in the sense defined in section 2.3, then it has no choice but to try one of the actions at random. This sad situation is discussed in Chapter 4. But suppose the agent has a map of Romania. The point of a map is to provide the agent with information about the states it might get itself into and the actions it can take. The agent can use this information to consider subsequent stages of a hypothetical journey via each of the 3 towns, trying to find a journey that eventually gets to Bucharest. Once it has found a path on the map from Arad to Bucharest, it can achieve its goal by carrying out the driving actions that correspond to the lengths of the journey. In general, an agent with several immediate options of unknown value can decide what to do by first examining future actions that eventually lead to states of known value. To be more specific about what we mean by examining future actions, we have to be more specific about properties of the environment, as defined in section 2.3. For now, 1. We are assuming that most readers are in the same position and can easily imagine themselves to be as clueless as our agent. We apologize to Romanian readers who are unable to take advantage of this pedagogical device. 66 Chapter 3. Solving problems by searching. We assume that the environment is observable, so the agent always knows the current state. For the agent driving in Romania, it's reasonable to suppose that each city on the map has a sign indicating its presence to arriving drivers. We also assume the environment is discrete, so at any given state there are only finitely many actions to choose from. This is true for navigating in Romania because each city is connected to a small number of other cities. We will assume the environment is known, so the agent knows which states are reached by each action. Having an accurate map suffices to meet this condition for navigation problems. Finally, we assume that the environment is deterministic, so each action has exactly one outcome. Under ideal conditions, this is true for the agent in Romania. It means that if it chooses to drive from Arad to Sibiu, it does end up in Sibiu. Of course, conditions are not always ideal, as we show in Chapter 4. Under these assumptions, the solution to any problem is a fixed sequence of actions. Of course, one might say, what else could it be? Well, in general it could be a branching strategy that recommends different actions in the future depending on what precepts arrive. For example, under less than ideal conditions, the agent might plan to drive from Arad to Sibiu and then to Râmnică-Vâlcea, but may also need to have a contingency plan in case it arrives by accident in Zerand instead of Sibiu. Fortunately, if the agent knows the initial state and the environment is known and deterministic, it knows exactly where it will be after the first action and what it will perceive. Since only one percept is possible after the first action, the solution can specify only one possible second action, and so on. Search. The process of looking for a sequence of actions that reaches the goal is called search. Solution. A search algorithm takes a problem as input and returns a solution in the form of an action sequence. Once a solution is found, the actions it recommends can be carried out. This execution is called the execution phase. Thus, we have a simple formulate, search, execute design for the agent, as shown in figure 3.1. After formulating a goal and a problem to solve, the agent calls a search procedure to solve it. It then uses the solution to guide its actions, doing whatever the solution recommends as the next thing to do, typically the first action of the sequence, and then removing that step from the sequence. Once the solution has been executed, the agent will formulate a new goal. Notice that while the agent is executing the solution sequence, it ignores its precepts when choosing an action because it knows in advance what they will be. An agent that carries out its plans with its eyes closed, so to speak, must be quite certain of what is going open loop on. Control theorists call this an open loop system, because ignoring the precepts breaks the loop between agent and environment. We first describe the process of problem formulation, and then devote the bulk of the chapter to various algorithms for the search function. We do not discuss the workings of the update state and formulate goal functions further in this chapter. 3.1.1 Well-defined problems and solutions. Problem. A problem can be defined formally by 5 components. Initial state. The initial state that the agent starts in. For example, the initial state for our agent in Romania might be described as in Arad. Section 3.1. Problem-solving agent 67. Function. Simple problem-solving agent, percept, returns an action persistent, sec, an action sequence, initially empty state, some description of the current world state, goal, a goal, initially null problem, a problem formulation. State leftward arrow update state, percept, if sec is empty then goal leftward arrow formulate goal, state, problem leftward arrow formulate problem, state, goal. Sec leftward arrow search, problem, if sec equals failure then return a null action leftward arrow first, sec. Sec leftward arrow rest, sec, return action. Figure 3.1 A simple problem-solving agent. It first formulates a goal and a problem, searches for a sequence of actions that would solve the problem, and then executes the actions one at a time. When this is complete, it formulates another goal and starts over. Actions. A description of the possible actions available to the agent. Given a particular state S, actions, S, returns the set of actions that can be executed in S. We say that each of applicable these actions is applicable in S. For example, from the state in Arad, the applicable actions are go, Sibiu, go, Timișoara, go, Zerand. A description of what each action does, the formal name for this is the transition. Transition model, specified by a function result, S, A, that returns the state that results from successor doing action and state S. We also use the term successor to refer to any state reachable from a given state by a single action point. For example, we have result, in, Arad, go, Zerand, equals in, Zerand. State space. Together, the initial state, actions, and transition model implicitly define the state space of the problem, the set of all states reachable from the initial state by any sequence. Graph of actions. The state space forms a directed network or graph in which the nodes are states and the links between nodes are actions. The map of Romania shown in figure 3.2 can be interpreted as a state space graph if we view each road as standing path for 2 driving actions, one in each direction. A path in the state space is a sequence of states connected by a sequence of actions. Goal test. The goal test, which determines whether a given state is a goal state. Sometimes there is an explicit set of possible goal states, and the test simply checks whether the given state is one of them. The agent's goal in Romania is the singleton set in Bucharest. Too many treatments of problem solving, including previous editions of this book, use a successor function, which returns the set of all successors, instead of separate actions and result functions. The successor function makes it difficult to describe an agent that knows what actions it can try but not what they achieve. Also, note some author use result, A, S, instead of result, S, A, and some use do instead of result. 68 Chapter 3. Solving problems by searching. Georgio. Erdesani Hersova. Efori. Niam Oradia. Zerand Arad. Timișoara Logaje. Mahadaya. Drobita Craiova. Sibiu Fagaras. Vitesti. Vaslui. Yash. Rymnica-Vilsa. Bucharest. 71. 75. 118. 111 70. 75 120. 151 140 99 80. 97. 101. 211. 138 146 85. 90. 98. 142. 92. 87. 86. Figure 3.2 A simplified road map of part of Romania. Sometimes the goal is specified by an abstract property rather than an explicitly enumerated set of states. For example, in chess, the goal is to reach a state called checkmate, where the opponent's king is under attack and can't escape. Path cost: a path cost function that assigns a numeric cost to each path. The problem-solving agent chooses a cost function that reflects its own performance measure. For the agent trying to get to Bucharest, time is of the essence, so the cost of a path might be its length in kilometers. In this chapter, we assume that the cost of a path can be described as the sum of the costs of the individual actions along the path. 3 Step cost: the step cost of taking action in state S to reach state S is denoted by C, S, A, S. The step costs for Romania are shown in figure 3.2 as route distances. We assume that step costs are non-negative. 4 The preceding elements define a problem and can be gathered into a single data structure. That is given as input to a problem-solving algorithm. A solution to a problem is an action sequence that leads from the initial state to a goal state. Solution quality is measured by the optimal solution path cost function, and an optimal solution has the lowest path cost among all solutions. 3.1.2 Formulating problems. In the preceding section we proposed a formulation of the problem of getting to Bucharest in terms of the initial state, actions, transition model, goal test, and path cost. This formulation seems reasonable, but it is still a model and abstract mathematical description and not the three. This assumption is algorithmically convenient but also theoretically justifiable. See page 649 in chapter 17. 4 The implications of negative costs are explored in exercise 3.8. Section 3.2. Example problem 69. Real thing. Compare the simple state description we have chosen, in Arad, to an actual cross-country trip, where the state of the world includes so many things: the traveling companions, the current radio program, the scenery out of the window, the proximity of law enforcement officers, the distance to the next rest stop, the condition of the road, the weather, and so on. All these considerations are left out of our state descriptions because they are irrelevant to the problem of finding a route to Bucharest. The process of removing detail from a representation abstraction is called abstraction. In addition to abstracting the state description, we must abstract the actions themselves. A driving action has many effects. Besides changing the location of the vehicle and its occupants, it takes up time, consumes fuel, generates pollution, and changes the agent. As they say, travel is broadening. Our formulation takes into account only the change in location. Also, there are many actions that we omit altogether: turning on the radio, looking out of the window, slowing down for law enforcement officers, and so on. And of course, we don't specify actions at the level of turn steering wheel to the left by 1 degree. Can we be more precise about defining the appropriate level of abstraction? Think of the abstract states and actions we have chosen as corresponding to large sets of detailed world states and detailed action sequences. Now consider a solution to the abstract problem, for example, the path from Arad to Sibiu to Rymnica-Vilsa to Pitești to Bucharest. This abstract solution corresponds to a large number of more detailed paths. For example, we could drive with the radio on between Sibiu and Rymnica-Vilsa, and then switch it off for the rest of the trip. The abstraction is valid if we can expand any abstract solution into a solution in the more detailed world. A sufficient condition is that for every detailed state that is in Arad, there is a detailed path to some state that is in Sibiu, and so on. 5 The abstraction is useful if carrying out each of the actions in the solution is easier than the original problem. In this case they are easy enough that they can be carried out without further search or planning by an average driving agent. The choice of a good abstraction thus involves removing as much detail as possible while retaining validity and ensuring that the abstract actions are easy to carry out. Were it not for the ability to construct useful abstractions, intelligent agents would be completely swamped by the real world. 3.2 Example problems. The problem-solving approach has been applied to a vast array of task environments. We list some of the best known here, distinguishing between toy and real-world problems. A toy problem is intended to illustrate or exercise various problem-solving methods. It can be given a concise, exact description and hence is usable by different researchers to compare the performance of algorithms. A real-world problem is one whose solutions people actually real-world problem care about. Such problems tend not to have a single agreed-upon description, but we can give the general flavor of their formulations. 5 See section 11.2 for a more complete set of definitions and algorithms. 70 Chapter 3. Solving problems by searching. R. LSS. SS. R. L. R. L. R. L. S. SS. S. L. L. LLR. R. 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 Figure 3.3 The state space for the vacuum world. Links denote actions: L equals left, R equals right, S equals suck. 3.2.1 Toy problems. The first example we examine is the vacuum world, first introduced in chapter 2. See figure 2.2. This can be formulated as a problem as follows. States: the state is determined by both the agent location and the dirt locations. The agent is in one of two locations, each of which might or might not contain dirt. Thus, there are 2 times 22 equals 8 possible world states. A larger environment with n locations has n to n states. Initial state: any state can be designated as the initial state. Actions: in this simple environment, each state has just 3 actions: left, right, and suck. Larger environments might also include up and down. Transition model: the actions have their expected effects, except that moving left in the leftmost square, moving right in the rightmost square, and sucking in a clean square have no effect. The complete state space is shown in figure 3.3. Goal test: this checks whether all the squares are clean. Path cost: each step costs 1, so the path cost is the number of steps in the path. Compared with the real world, this toy problem has discrete locations, discrete dirt, reliable cleaning, and it never gets any dirtier. Chapter 4 relaxes some of these assumptions. 8 Puzzle. The 8 puzzle, an instance of which is shown in figure 3.4, consists of a 3x3 board with 8 numbered tiles and a blank space. A tile adjacent to the blank space can slide into the space. The object is to reach a specified goal state, such as the one shown on the right of the figure. The standard formulation is as follows. Section 3.2. Example problem 71. 2. Start state goal state. 1. 3 4. 6 7. 5. 1. 2. 3. 4. 6. 7. 8. 5. 8. Figure 3.4 a typical instance of the 8 puzzle. States, a state description specifies the location of each of the 8 tiles and the blank in one of the 9 squares. Initial state, any state can be designated as the initial state. Note that any given goal can be reached from exactly half of the possible initial states, exercise 3.4. Actions, the simplest formulation defines the actions as movements of the blank space left, right, up, or down. Different subsets of these are possible depending on where the blank is. Transition model, given a state and action, this returns the resulting state. For example, if we apply left to the start state in figure 3.4, the resulting state has the 5 and the blank switched. Goal test, this checks whether the state matches the goal configuration shown in figure 3.4. Other goal configurations are possible. Path cost, each step costs 1, so the path cost is the number of steps in the path. What abstractions have we included here? The actions are abstracted to their beginning and final states, ignoring the intermediate locations where the block is sliding. We have abstracted away actions such as shaking the board when pieces get stuck and ruled out extracting the pieces with a knife and putting them back again. We are left with a description of the rules of the puzzle, avoiding all the details of physical manipulations. The 8 puzzle belongs to the family of sliding block puzzles, which are often used as sliding block puzzles test problems for new search algorithms in AI. This family is known to be NP-complete, so one does not expect to find methods significantly better in the worst case than the search algorithms described in this chapter and the next. The 8 puzzle has 9/2 equals 181, 440 reachable states and is easily solved. The 15 puzzle, on a 4x4 board, has around 1.3 trillion states, and random instances can be solved optimally in a few milliseconds by the best search algorithms. The 24 puzzle, on a 5x5 board, has around 1025 states, and random instances take several hours to solve optimally. 8 queens problem. The goal of the 8 queens problem is to place 8 queens on a chessboard such that no queen attacks any other. A queen attacks any piece in the same row, column, or diagonal. Figure 3.5 shows an attempted solution that fails. The queen in the rightmost column is attacked by the queen at the top left. 72 Chapter 3. Solving problems by searching. Figure 3.5 almost a solution to the 8 queens problem. Solution is left as an exercise. Although efficient special purpose algorithms exist for this problem and for the whole n queens family, it remains a useful test problem for search algorithms. There are 2 main kinds of formulation. An incremental formulation involves operators that augment the state incremental formulation description, starting with an empty state. For the 8 queens problem, this means that each action adds a queen to the state. A complete state formulation starts with all 8 queens on complete state formulation the board and moves them around. In either case, the path cost is of no interest because only the final state counts. The first incremental formulation one might try is the following. States, any arrangement of 0 to 8 queens on the board is a state. Initial state, no queens on the board. Actions, add a queen to any empty square. Transition model, returns the board with a queen added to the specified square. Goal test, 8 queens are on the board, none attacked. In this formulation, we have 64, 63, 57, 1.8 times 1014 possible sequences to investigate. A better formulation would prohibit placing a queen in any square that is already attacked. States, all possible arrangements of n queens, 0 less than or equal to n less than or equal to 8, 1 per column in the leftmost n columns, with no queen attacking another. Actions, add a queen to any square in the leftmost empty column such that it is not attacked by any other queen. This formulation reduces the 8 queen state space from 1.8 times 1014 to just 2057, and solutions are easy to find. On the other hand, for 100 queens the reduction is from roughly 10,400 states to about 1052 states, exercise 3.5, a big improvement, but not enough to make the problem tractable. Section 4.1 describes the complete state formulation, and Chapter 6 gives a simple algorithm that solves even the million queens problem with ease. Section 3.2. Example problem 73. Our final toy problem was devised by Donald Knuth, 1964, and illustrates how infinite state spaces can arise. Knuth conjectured that, starting with the number 4, a sequence of factorial, square root, and floor operations will reach any desired positive integer. For example, we can reach 5 from 4 as follows: 4 equals 5. The problem definition is very simple. States, positive numbers. Initial state, 4. Actions, apply factorial, square root, or floor operation, factorial for integers only. Transition model, as given by the mathematical definitions of the operations. Goal test, state is the desired positive integer. To our knowledge there is no bound on how large a number might be constructed in the process of reaching a given target. For example, the number 620, 448, 401, 733, 239, 439, 360, 000 is generated in the expression for 5, so the state space for this problem is infinite. Such state spaces arise frequently in tasks involving the generation of mathematical expressions, circuits, proofs, programs, and other recursively defined objects. 3.2.2 Real-world problems. We have already seen how the root finding problem is defined in terms of specified local root finding problems and transitions along links between them. Root finding algorithms are used in a variety of applications. Some, such as websites and in-car systems that provide driving directions, are relatively straightforward extensions of the Romania example. Others, such as routing video streams in computer networks, military operations planning, and airline travel planning systems, involve much more complex specifications. Consider the airline travel problems that must be solved by a travel planning website. States, each state obviously includes a location, example an airport, and the current time. Furthermore, because the cost of an action, a flight segment, may depend on previous segments, their fare bases, and their status as domestic or international, the state must record extra information about these historical aspects. Initial state, this is specified by the user's query. Actions: take any flight from the current location, in any seat class, leaving after the current time, leaving enough time for within airport transfer if needed. Transition model: the state resulting from taking a flight will have the flight's destination as the current location and the flight's arrival time as the current time. Goal test: are we at the final destination specified by the user? Path cost: this depends on monetary cost, waiting time, flight time, customs and migration procedures, seat quality, time of day, type of airplane, frequent flyer mileage awards, and so on. 74 Chapter 3. Solving problems by searching. Commercial travel advice systems use a problem formulation of this kind, with many additional complications to handle the Byzantine fare structures that airlines impose. Any season traveler knows, however, that not all air travel goes according to plan. A really good system should include contingency plans such as backup reservations on alternate flights to the extent that these are justified by the cost and likelihood of failure of the original plan. Touring problems are closely related to route finding problems, but with an important difference. Consider, for example, the problem visit every city in Figure 3.2 at least once, starting and ending in Bucharest. As with route finding, the actions correspond to trips between adjacent cities. The state space, however, is quite different. Each state must include not just the current location but also the set of cities the agent has visited. So the initial state would be in Bucharest, visited, Bucharest. A typical intermediate state would be in Vaslui, visited, Bucharest, Ertisani, Vaslui, and the goal test would check whether the agent is in Bucharest and all 20 cities have been visited. The traveling salesperson problem, TSP, is a touring problem in which each city traveling salesperson problem must be visited exactly once. The aim is to find the shortest tour. The problem is known to be NP hard, but an enormous amount of effort has been expended to improve the capabilities of TSP algorithms. In addition to planning trips for traveling salespersons, these algorithms have been used for tasks such as planning movements of automatic circuit board drills and of stocking machines on shop floors. VLSI layout. A VLSI layout problem requires positioning millions of components and connections on a chip to minimize area, minimize circuit delays, minimize stray capacitances, and maximize manufacturing yield. The layout problem comes after the logical design phase and is usually split into two parts, cell layout and channel routing. In cell layout, the primitive components of the circuit are grouped into cells, each of which performs some recognized function. Each cell has a fixed footprint, size and shape, and requires a certain number of connections to each of the other cells. The aim is to place the cells on the chip so that they do not overlap and so that there is room for the connecting wires to be placed between the cells. Channel routing finds a specific route for each wire through the gaps between the cells. These search problems are extremely complex, but definitely worth solving. Later in this chapter, we present some algorithms capable of solving them. Robot navigation. Robot navigation is a generalization of the route finding problem described earlier. Rather than following a discrete set of routes, a robot can move in a continuous space with, in principle, an infinite set of possible actions and states. For a circular robot moving on a flat surface, the space is essentially two-dimensional. When the robot has arms and legs or wheels that must also be controlled, the search space becomes many-dimensional. Advanced techniques are required just to make the search space finite. We examine some of these methods in Chapter 25. In addition to the complexity of the problem, real robots must also deal with errors in their sensor readings and motor controls. Automatic assembly sequencing of complex objects by a robot was first demonstrated. Automatic assembly sequencing by Freddie, Mickey, 1972. Progress since then has been slow but sure, to the point where the assembly of intricate objects such as electric motors is economically feasible. In assembly problems, the aim is to find an order in which to assemble the parts of some object. If the wrong order is chosen, there will be no way to add some part later in the sequence without. Section 3.3. Searching for solution 75. Undoing some of the work already done. Checking a step in the sequence for feasibility is a difficult geometrical search problem closely related to robot navigation. Thus, the generation of legal actions is the expensive part of assembly sequencing. Any practical algorithm must avoid exploring all but a tiny fraction of the state space. Another important assembly problem, protein design, is protein design, in which the goal is to find a sequence of amino acids that will fold into a three-dimensional protein with the right properties to cure some disease. 3.3 Searching for solutions. Having formulated some problems, we now need to solve them. A solution is an action sequence, so search algorithms work by considering various possible action sequences. The search tree possible action sequences starting at the initial state form a search tree with the initial state node at the root. The branches are actions and the nodes correspond to states in the state space of the problem. Figure 3.6 shows the first few steps in growing the search tree for finding a route from Arad to Bucharest. The root node of the tree corresponds to the initial state, in Arad. The first step is to test whether this is a goal state. Clearly it is not, but it is important to check so that we can solve trick problems like starting in Arad, get to Arad. Then we expanding need to consider taking various actions. We do this by expanding the current state, that is, applying each legal action to the current state, thereby generating a new set of states. In parent node this case, we add three branches from the parent node in Arad, leading to three new child node nodes, in Sibiu, in Timișoara, and in Zerand. Now we must choose which of these three possibilities to consider further. This is the essence of search, following up one option now and putting the others aside for later, in case the first choice does not lead to a solution. Suppose we choose Sibiu first. We check to see whether it is a goal state, it is not, and then expand it to get in Arad, in Făgăraș, in Oradea, and in Râmnicu-Vâlcea. We can then choose any of these four or go leaf node back and choose Timișoara or Zerand. Each of these 6 nodes is a leaf node, that is, a node with no children in the tree. The set of all leaf nodes available for expansion at any given frontier point is called the frontier. Many authors call it the open list, which is both geographically open list less evocative and less accurate, because other data structures are better suited than a list. In Figure 3.6, the frontier of each tree consists of those nodes with bold outlines. The process of expanding nodes on the frontier continues until either a solution is found or there are no more states to expand. The general tree search algorithm is shown informally in Figure 3.7. Search algorithms all share this basic structure. They vary primarily search strategy according to how they choose which state to expand next, the so-called search strategy. The eagle-eyed reader will notice one peculiar thing about the search tree shown in Figure 3.6, it includes the path from Arad to Sibiu and back to Arad again. We say that in Arad, repeated state is a repeated state in the search tree, generated in this case by a loop path. Considering loop paths, such loop paths means that the complete search tree for Romania is infinite because there is no limit to how often one can traverse a loop. On the other hand, the state space, the map shown in figure 3.2, has only 20 states. As we discuss in section 3.4, loops can cause 76 chapter 3. Solving problems by searching certain algorithms to fail, making otherwise solvable problems unsolvable. Fortunately, there is no need to consider loop paths. We can rely on more than intuition for this, because path costs are additive and step costs are non-negative. A loop path to any given state is never better than the same path with the loop removed. Redundant path loop paths are a special case of the more general concept of redundant paths, which exist whenever there is more than one way to get from one state to another. Consider the paths Arad, Sibiu, 140 kilometers long, and Arad, Zerand, Oradea, Sibiu, 297 kilometers long. Obviously, the second path is redundant, it's just a worse way to get to the same state. If you are concerned about reaching the goal, there's never any reason to keep more than one path to any given state, because any goal state that is reachable by extending one path is also reachable by extending the other. In some cases, it is possible to define the problem itself so as to eliminate redundant paths. For example, if we formulate the 8 queens problem, page 71, so that a queen can be placed in any column, then each state with n queens can be reached by n different paths, but if we reformulate the problem so that each new queen is placed in the leftmost empty column, then each state can be reached only through one path. A. The initial state. B. After expanding Arad. C. After expanding Sibiu. Arad Fagaras Oradea Rimnicovilsa Arad Lugaje Arad Oradea. Rimnicovilsa Lugaje. Sibiu Zerand. Arad Fagaras Oradea. Timishwara. Arad Arad Oradea. Arad Lugaje Arad Oradea. Zerand. Arad. Sibiu Timishwara. Arad. Rimnicovilsa. Zerand. Arad. Sibiu. Arad Fagaras Oradea. Timishwara. Figure 3.6 Partial search trees for finding a route from Arad to Bucharest. Nodes that have been expanded are shaded, nodes that have been generated but not yet expanded are outlined in bold, nodes that have not yet been generated are shown in faint dashed lines. Section 3.3. Searching for solution 77. Function tree search, problem, returns a solution, or failure. Initialize the frontier using the initial state of problem loop. Do if the frontier is empty, then return failure. Choose a leaf node and remove it from the frontier. If the node contains a goal state, then return the corresponding solution. Expand the chosen node, adding the resulting nodes to the frontier. Function graph search, problem, returns a solution, or failure. Initialize the frontier using the initial state of problem. Initialize the explored set to be empty loop. Do if the frontier is empty, then return failure. Choose a leaf node and remove it from the frontier. If the node contains a goal state, then return the corresponding solution. Add the node to the explored set. Expand the chosen node, adding the resulting nodes to the frontier only if not in the frontier or explored set. Figure 3.7. An informal description of the general tree search and graph search algorithms. The parts of graph search marked in bold italic are the additions needed to handle repeated states. In other cases, redundant paths are unavoidable. This includes all problems where the actions are reversible, such as route finding problems and sliding block puzzles. Route. Rectangular grid. Finding on a rectangular grid, like the one used later for figure 3.9, is a particularly important example in computer games. In such a grid, each state has 4 successors, so a search tree of depth d that includes repeated states has 4 d leaves, but there are only about 2 distinct states within d steps of any given state. 4d equals 20, this means about a trillion nodes but only about 800 distinct states. Thus, following redundant paths can cause a tractable problem to become intractable. This is true even for algorithms that know how to avoid infinite loops. As the saying goes, algorithms that forget their history are doomed to repeat it. The way to avoid exploring redundant paths is to remember where one has been. To do this, we explored set augment the tree search algorithm with a data structure called the explored set, also closed list known as the closed list, which remembers every expanded node. Newly generated nodes that match previously generated nodes ones in the explored set or the frontier can be discarded instead of being added to the frontier. The new algorithm, called graph search, is shown informally in figure 3.7. The specific algorithms in this chapter draw on this general design. Clearly, the search tree constructed by the graph search algorithm contains at most one copy of each state, so we can think of it as growing a tree directly on the state space graph. Separator as shown in figure 3.8. The algorithm has another nice property. The frontier separates the state space graph into the explored region and the unexplored region, so that every path from 78 chapter 3. Solving problems by searching. Figure 3.8. A sequence of search trees generated by a graph search on the Romania problem of figure 3.2. At each stage, we have extended each path by one step. Notice that at the third stage, the northernmost city, Oradea, has become a dead end. Both of its successors are already explored by other paths. A, B, C. Figure 3.9. The separation property of graph search, illustrated on a rectangular grid problem. The frontier, white nodes, always separates the explored region of the state space, black nodes, from the unexplored region, gray nodes. In A, just the route has been expanded. In B, one leaf node has been expanded. In C, the remaining successors of the route have been expanded in clockwise order. The initial state to an unexplored state has to pass through a state in the frontier. If this seems completely obvious, try exercise 3.13 now. This property is illustrated in figure 3.9. As every step moves a state from the frontier into the explored region while moving some states from the unexplored region into the frontier, we see that the algorithm is systematically examining the states in the state space, one by one, until it finds a solution. 3.3.1 Infrastructure for search algorithms. Search algorithms require a data structure to keep track of the search tree that is being constructed. For each node n of the tree, we have a structure that contains 4 components. N.state, the state in the state space to which the node corresponds. N.parent, the node in the search tree that generated this node. N.action, the action that was applied to the parent to generate the node. N.path cost, the cost, traditionally denoted by G, N, of the path from the initial state to the node, as indicated by the parent pointers. Section 3.3. Searching for solution 79. 1. 3 2. 5 4. 6. 7. 1 8. 3 2. 5 4. 6. 7. 8. Node. State. Parent. Action equals right path cost equals 6. Figure 3.10 nodes are the data structures from which the search tree is constructed. Each has a parent, a state, and various bookkeeping fields. Arrows point from child to parent. Given the components for a parent node, it is easy to see how to compute the necessary components for a child node. The function child node takes a parent node and an action and returns the resulting child node. Function child node, problem, parent, action, return a node with state equals problem.result, parent.state, action, parent equals parent, action equals action, path cost equals parent.path cost plus problem.step cost, parent.state, action. The node data structure is depicted in figure 3.10. Notice how the parent pointers string the nodes together into a tree structure. These pointers also allow the solution path to be extracted when a goal node is found. We use the solution function to return the sequence of actions obtained by following parent pointers back to the root. Up to now, we have not been very careful to distinguish between nodes and states, but in writing detailed algorithms it's important to make that distinction. A node is a bookkeeping data structure used to represent the search tree. A state corresponds to a configuration of the world. Thus, nodes are on particular paths, as defined by parent pointers, whereas states are not. Furthermore, two different nodes can contain the same world state if that state is generated via two different search paths. Now that we have nodes, we need somewhere to put them. The frontier needs to be stored in such a way that the search algorithm can easily choose the next node to expand. Queue according to its preferred strategy. The appropriate data structure for this is a queue. The operations on a queue are as follows. Empty, queue, returns true only if there are no more elements in the queue. Pop, queue, removes the first element of the queue and returns it. Insert, element, queue, inserts an element and returns the resulting queue. 80 Chapter 3. Solving problems by searching. Queues are characterized by the order in which they store the inserted nodes. Three common FIFOQ variants are the first in, first out, or FIFOQ, which pops the oldest element of the queue, LIFOQ the last in, first out, or LIFOQ, also known as a stack, which pops the newest element priority queue of the queue, and the priority queue, which pops the element of the queue with the highest priority according to some ordering function. The explored set can be implemented with a hash table to allow efficient checking for repeated states. With a good implementation, insertion and lookup can be done in roughly constant time no matter how many states are stored. One must take care to implement the hash table with the right notion of equality between states. For example, in the traveling salesperson problem, page 74, the hash table needs to know that the set of visited cities Bucharest, Erdőszini, Vaslui is the same as Erdőszini, Vaslui, Bucharest. Sometimes this can be achieved most easily by insisting that the data structures for states be in some canonical form, that is, logically equivalent states should map to the same data structure. In the case of states described by sets, for example, a bit vector representation or a sorted list without repetition would be canonical, whereas an unsorted list would not. 3.3.2 Measuring problem solving performance. Before we get into the design of specific search algorithms, we need to consider the criteria that might be used to choose among them. We can evaluate an algorithm's performance in four ways. Completeness. Completeness. Is the algorithm guaranteed to find a solution when there is one? Optimality. Optimality. Does the strategy find the optimal solution, as defined on page 68? Time complexity. Time complexity. How long does it take to find a solution? Space complexity. Space complexity. How much memory is needed to perform the search? Time and space complexity are always considered with respect to some measure of the problem difficulty. In theoretical computer science, the typical measure is the size of the state space graph, V plus E, where V is the set of vertices, nodes, of the graph and E is the set of edges, links. This is appropriate when the graph is an explicit data structure that is input to the search program. The map of Romania is an example of this. In AI, the graph is often represented implicitly by the initial state, actions, and transition model and is frequently infinite. For these reasons, complexity is expressed in terms of three quantities: B, the branching factor or maximum number of successors of any node; D, the depth of the shallowest goal depth node, i.e., the number of steps along the path from the root; and M, the maximum length of any path in the state space. Time is often measured in terms of the number of nodes generated during the search, and space in terms of the maximum number of nodes stored in memory. For the most part, we describe time and space complexity for search on a tree. For a graph, the answer depends on how redundant the paths in the state space are. Search cost. To assess the effectiveness of a search algorithm, we can consider just the search cost, which typically depends on the time complexity but can also include a term for memory total cost usage, or we can use the total cost, which combines the search cost and the path cost of the solution found. For the problem of finding a route from Arad to Bucharest, the search cost is the amount of time taken by the search and the solution cost is the total length of the path. Section 3.4. Uninformed search strategies. 81. In kilometers. Thus, to compute the total cost, we have to add milliseconds and kilometers. There is no official exchange rate between the two, but it might be reasonable in this case to convert kilometers into milliseconds by using an estimate of the car's average speed, because time is what the agent cares about. This enables the agent to find an optimal trade-off point at which further computation to find a shorter path becomes counterproductive. The more general problem of trade-offs between different goods is taken up in Chapter 16. 3.4 Uninformed search strategies. This section covers several search strategies that come under the heading of uninformed search, also called blind search. The term means that the strategies have no additional uninformed search blind search information about states beyond that provided in the problem definition. All they can do is generate successors and distinguish a goal state from a non-goal state. All search strategies are distinguished by the order in which nodes are expanded. Strategies that know whether informed search one non-goal state is more promising than another are called informed search or heuristic search strategies. They are covered in section 3.5. 3.4.1 Breadth first search. Breadth first search is a simple strategy in which the root node is expanded first, then all the breadth first search successors of the root node are expanded next, then their successors, and so on. In general, all the nodes are expanded at a given depth in the search tree before any nodes at the next level are expanded. Breadth first search is an instance of the general graph search algorithm, figure 3.7, in which the shallowest unexpanded node is chosen for expansion. This is achieved very simply by using a FIFOQ for the frontier. Thus, new nodes, which are always deeper than their parents, go to the back of the queue, and old nodes, which are shallower than the new nodes, get expanded first. There is one slight tweak on the general graph search algorithm, which is that the goal test is applied to each node when it is generated rather than when it is selected for expansion. This decision is explained below, where we discuss time complexity. Note also that the algorithm, following the general template for graph search, discards any new path to a state already in the frontier or explored set. It is easy to see that any such path must be at least as deep as the one already found. Thus, breadth-first search always has the shallowest path to every node on the frontier. Pseudocode is given in Figure 3.11. Figure 3.12 shows the progress of the search on a simple binary tree. How does breadth-first search rate according to the 4 criteria from the previous SE session? We can easily see that it is complete if the shallowest goal node is at some finite depth d. Breadth-first search will eventually find it after generating all shallower nodes, provided the branching factor b is finite. Note that as soon as a goal node is generated, we know it is the shallowest goal node because all shallower nodes must have been generated already and failed the goal test. Now, the shallowest goal node is not necessarily the optimal one. 82 Chapter 3. Solving problems by searching. Function breadth-first search, problem, returns a solution, or failure. Node leftward arrow a node with state equals problem.initial state, path cost equals 0 if problem.goal test, node.state, then return solution, node, frontier leftward arrow FIFOQ with node as the only element explored leftward arrow and empty set loop do if empty, frontier, then return failure node leftward arrow pop, frontier, / asterisk chooses the shallowest node in frontier * add node.state to explored for each action in problem.actions, node.state, do child leftward arrow child node, problem, node, action, if child.state is not in explored or frontier then. If problem.goal test, child.state, then return solution, child, frontier leftward arrow insert, child frontier. Figure 3.11 breadth-first search on a graph. Technically, breadth-first search is optimal if the path cost is a non-decreasing function of the depth of the node. The most common such scenario is that all actions have the same cost. So far, the news about breadth-first search has been good. The news about time and space is not so good. Imagine searching a uniform tree where every state has b successors. The root of the search tree generates b nodes at the first level, each of which generates b more nodes, for a total of b2 at the second level. Each of these generates b more nodes, yielding b3 nodes at the third level, and so on. Now suppose that the solution is at depth d. In the worst case, it is the last node generated at that level. Then the total number of nodes generated is b plus b2 plus b3 plus bd equals o, bd. If the algorithm were to apply the goal test to nodes when selected for expansion, rather than when generated, the whole layer of nodes at depth d would be expanded before the goal was detected and the time complexity would be o, bd plus 1, dot. As for space complexity, for any kind of graph search, which stores every expanded node in the explored set, the space complexity is always within a factor of b of the time complexity. For breadth-first graph search in particular, every node generated remains in memory. There will be o, bd1, nodes in the explored set and o, bd, nodes in the frontier. A, b, c, d, e, f, g, a, b, d, e, f, g, c, a, c, d, e, f, g, b, c, b, d, e, f, g, a. Figure 3.12 breadth-first search on a simple binary tree. At each stage, the node to be expanded next is indicated by a marker. Section 3.4. Uninformed search strategies 83. So the space complexity is O, BD, i.e., it is dominated by the size of the frontier. Switching to a tree search would not save much space, and in a state space with many redundant paths, switching could cost a great deal of time. An exponential complexity bound such as O, BD, is scary. Figure 3.13 shows why. It lists, for various values of the solution depth d, the time and memory required for a breadth-first search with branching factor b equals 10. The table assumes that 1 million nodes can be generated per second and that a node requires 1000 bytes of storage. Many search problems fit roughly within these assumptions, give or take a factor of 100, when run on a modern personal computer. Depth nodes time memory. 110.11 milliseconds 107 kilobytes for 11,110 11 milliseconds 10.6 megabytes 6 106 1.1 seconds 1 gigabyte 8 108 2 minutes 103 gigabytes 10 1010 3 hours 10 terabytes 12 1012 13 days 1 petabyte 14 1014 3.5 years 99 petabytes 16 1016 350 years 10 exabytes. Figure 3.13 time and memory requirements for breadth-first search. The numbers shown assume branching factor b equals 10, 1 million nodes / second, 1000 bytes / node. 2 lessons can be learned from figure 3.13. First, the memory requirements are a bigger problem for breadth-first search than is the execution time. One might wait 13 days for the solution to an important problem with search depth 12, but no personal computer has the petabyte of memory it would take. Fortunately, other strategies require less memory. The second lesson is that time is still a major factor. If your problem has a solution at depth 16, then, given our assumptions, it will take about 350 years for breadth-first search, or indeed any uninformed search, to find it. In general, exponential complexity search problems cannot be solved by uninformed methods for any but the smallest instances. 3.4.2 Uniform cost search. When all step costs are equal, breadth-first search is optimal because it always expands the shallowest unexpanded node. By a simple extension, we can find an algorithm that is optimal with any step cost function. Instead of expanding the shallowest node, uniform cost search expands the node n with the lowest path cost g, n. This is done by storing the frontier as a priority queue ordered by g. The algorithm is shown in figure 3.14. In addition to the ordering of the queue by path cost, there are 2 other significant differences from breadth-first search. The first is that the goal test is applied to a node when it is selected for expansion, as in the generic graph search algorithm shown in figure 3.7, rather than when it is first generated. The reason is that the first goal node that is generated. 84 Chapter 3. Solving problems by searching. Function uniform cost search, problem, returns a solution, or failure. Node leftward arrow a node with state equals problem.initial state, path cost equals 0 frontier leftward arrow a priority queue ordered by path cost, with node as the only element explored leftward arrow an empty set loop do if empty, frontier, then return failure node leftward arrow pop, frontier, / chooses the lowest cost node in frontier * if problem.goal test, node.state, then return solution, node, add node.state to explored for each action in problem.actions, node.state, do child leftward arrow child node, problem, node, action, if child.state is not in. Explored or frontier, then frontier, leftward arrow insert, child frontier, else if child.state is in frontier with higher path cost, then replace that frontier node with child. Figure 3.14 Uniform cost search on a graph. The algorithm is identical to the general graph search algorithm in figure 3.7, except for the use of a priority queue and the addition of an extra check in case a shorter path to a frontier state is discovered. The data structure for frontier needs to support efficient membership testing, so it should combine the capabilities of a priority queue and a hash table. Sibiu Fagaras. Vitesti. Rymnica-Vilsa. Bucharest. 99. 80. 97. 101. 211. Figure 3.15 part of the Romania state space, selected to illustrate uniform cost search. May be on a suboptimal path. The second difference is that a test is added in case a better path is found to a node currently on the frontier. Both of these modifications come into play in the example shown in figure 3.15, where the problem is to get from Sibiu to Bucharest. The successors of Sibiu are Rymnica-Vilsa and Fagaras, with costs 80 and 99, respectively. The least cost node, Rymnica-Vilsa, is expanded next, adding Vitesti with cost 80 plus 97 equals 177. The least cost node is now Fagaras, so it is expanded, adding Bucharest with cost 99 plus 211 equals 310. Now a goal node has been generated, but uniform cost search keeps going, choosing Vitesti for expansion and adding a second path. Section 3.4. Uninformed search strategies 85. To Bucharest with cost 80 plus 97 plus 101 equals 278. Now the algorithm checks to see if this new path is better than the old one. It is, so the old one is discarded. Bucharest, now with G cost 278, is selected for expansion and the solution is returned. It is easy to see that uniform cost search is optimal in general. First, we observe that whenever uniform cost search selects a node n for expansion, the optimal path to that node has been found. Were this not the case, there would have to be another frontier node n on the optimal path from the start node to n. By the graph separation property of figure 3.9, by definition, n would have lower g cost than n and would have been selected first. Then, because step costs are non-negative, paths never get shorter as nodes are added. These two facts together imply that uniform cost search expands nodes in order of their optimal path cost. Hence, the first goal node selected for expansion must be the optimal solution. Uniform cost search does not care about the number of steps a path has, but only about their total cost. Therefore, it will get stuck in an infinite loop if there is a path with an infinite sequence of zero-cost actions. For example, a sequence of no-op actions. 6 completeness is guaranteed provided the cost of every step exceeds some small positive constant. Uniform cost search is guided by path costs rather than depths, so its complexity is not easily characterized in terms of B and D. Instead, let C be the cost of the optimal solution 7. And assume that every action costs at least. Then the algorithm's worst-case time and space complexity is O, B1 plus C/, which can be much greater than BD. This is because uniform cost search can explore large trees of small steps before exploring paths involving large and perhaps useful steps. When all step costs are equal, B1 plus C/ is just BD plus 1. When all step costs are the same, uniform cost search is similar to breadth-first search, except that the latter stops as soon as it generates a goal, whereas uniform cost search examines all the nodes at the goal's depth to see if one has a lower cost. Thus uniform cost search does strictly more work by expanding nodes at depth D unnecessarily. 3.4.3 Depth-first search. Depth-first search always expands the deepest node in the current frontier of the search tree. Depth-first search. The progress of the search is illustrated in figure 3.16. The search proceeds immediately to the deepest level of the search tree, where the nodes have no successors. As those nodes are expanded, they are dropped from the frontier, so then the search backs up to the next deepest node that still has unexplored successors. The depth-first search algorithm is an instance of the graph search algorithm in figure 3.7, whereas breadth-first search uses FIFOQ, depth-first search uses LIFOQ. A LIFOQ means that the most recently generated node is chosen for expansion. This must be the deepest unexpanded node because it is one deeper than its parent, which, in turn, was the deepest unexpanded node when it was selected. As an alternative to the graph search style implementation, it is common to implement depth-first search with a recursive function that calls itself on each of its children in turn. A recursive depth-first algorithm incorporating a depth limit is shown in figure 3.17. 6 No-op, or no operation, is the name of an assembly language instruction that does nothing. 7 here, and throughout the book, the star in C means an optimal value for C. 86 Chapter 3. Solving problems by searching. ACFGMNO. ACFGLMNO. ACFGLMNO. CFGLMNO. ABCEFGKLMNO. ACEFGJKLMNO. ACEFGJKLMNO. ABCDEFGIJKLMNO. ABCDEFGHIJKLMNO. 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 Figure 3.16 Depth-first search on a binary tree. The unexplored region is shown in light gray. Explored nodes with no descendants in the frontier are removed from memory. Nodes at depth 3 have no successors and M is the only goal node. The properties of depth-first search depend strongly on whether the graph search or tree search version is used. The graph search version, which avoids repeated states and redundant paths, is complete in finite state spaces because it will eventually expand every node. The tree search version, on the other hand, is not complete. For example, in figure 3.6 the algorithm will follow the Arad, Sibiu loop forever. Depth-first tree search can be modified at no extra memory cost so that it checks new states against those on the path from the root to the current node. This avoids infinite loops in finite state spaces but does not avoid the proliferation of redundant paths. In infinite state spaces, both versions fail if an infinite non-goal path is encountered. For example, in Knuth's 4 problem, depth-first search would keep applying the factorial operator forever. For similar reasons, both versions are non-optimal. For example, in figure 3.16, depth-first search will explore the entire left subtree even if node C is a goal node. If node J were also a goal node, then depth-first search would return it as a solution instead of C, which would be a better solution. Hence, depth-first search is not optimal. Section 3.4. Uninformed search strategies 87. The time complexity of depth-first graph search is bounded by the size of the state space, which may be infinite, of course. A depth-first tree search, on the other hand, may generate all of the O, B, M nodes in the search tree, where M is the maximum depth of any node. This can be much greater than the size of the state space. Note that M itself can be much larger than D, the depth of the shallowest solution, and is infinite if the tree is unbounded. So far, depth-first search seems to have no clear advantage over breadth-first search, so why do we include it? The reason is the space complexity. For a graph search, there is no advantage, but a depth-first tree search needs to store only a single path from the root to a leaf node, along with the remaining unexpanded sibling nodes for each node on the path. Once a node has been expanded, it can be removed from memory as soon as all its descendants have been fully explored. See figure 3.16. For a state space with branching factor B and maximum depth M, depth-first search requires storage of only O, B, M nodes. Using the same assumptions as for figure 3.13 and assuming that nodes at the same depth as the goal node have no successors, we find that depth-first search would require 156 kilobytes instead of 10 exabytes at depth D equals 16, a factor of 7 trillion times less space. This has led to the adoption of depth-first tree search as the basic workhorse of many areas of AI, including constraint satisfaction, Chapter 6, propositional satisfiability, Chapter 7, and logic programming, Chapter 9. For the remainder of the section, we focus primarily on the tree search version of depth-first search. A variant of depth-first search called backtracking search uses still less memory. See backtracking search Chapter 6 for more details. In backtracking, only one successor is generated at a time rather than all successors. Each partially expanded node remembers which successor to generate next. In this way, only O, M memory is needed rather than O, B, M. Backtracking search facilitates yet another memory saving and time saving trick, the idea of generating a successor by modifying the current state description directly rather than copying it first. This reduces the memory requirements to just one state description and O, M actions. For this to work, we must be able to undo each modification when we go back to generate the next successor. For problems with large state descriptions, such as robotic assembly, these techniques are critical to success. 3.4.4 Depth-limited search. The embarrassing failure of depth-first search in infinite state spaces can be alleviated by supplying depth-first search with a predetermined depth limit. That is, nodes at depth are treated as if they have no successors. This approach is called depth-limited search. The depth-limited search depth limit solves the infinite path problem. Unfortunately, it also introduces an additional source of incompleteness if we choose D. Its time complexity is O, B, and its space complexity is O, B. Depth-first search can be viewed as a special case of depth-limited search with equals infinity. Sometimes, depth limits can be based on knowledge of the problem. For example, on the map of Romania there are 20 cities. Therefore, we know that if there is a solution, it must be of length 19 at the longest, so equals 19 is a possible choice. But in fact if we study the 88 Chapter 3, solving problems by searching function depth-limited search, problem, limit, returns a solution, or failure/cutoff return recursive DLS, make node, problem.initial state, problem, limit. Function recursive DLS, node, problem, limit, returns a solution, or failure/cutoff if problem.goalTest, node.state, then return solution, node, else if limit equals 0 then return cutoff else cutoff occurred, leftward arrow false for each action in problem.actions, node.state, do child leftward arrow child node, problem, node, action, result leftward arrow recursive DLS, child, problem, limit 1, if result equals cutoff then cutoff occurred, leftward arrow true else if result equals failure then return result if cutoff occurred. Then return cutoff else return failure. Figure 3.17 A recursive implementation of depth-limited tree search. Map carefully, we would discover that any city can be reached from any other city in at most diameter 9 steps. This number, known as the diameter of the state space, gives us a better depth limit, which leads to a more efficient depth-limited search. For most problems, however, we will not know a good depth limit until we have solved the problem. Depth-limited search can be implemented as a simple modification to the general tree or graph search algorithm. Alternatively, it can be implemented as a simple recursive algorithm as shown in figure 3.17. Notice that depth-limited search can terminate with two kinds of failure. The standard failure value indicates no solution, the cutoff value indicates no solution within the depth limit. 3.4.5 Iterative deepening depth-first search. Iterative deepening search, or iterative deepening depth-first search, is a general strategy, iterative deepening search often used in combination with depth-first tree search, that finds the best depth limit. It does this by gradually increasing the limit first 0, then 1, then 2, and so on until a goal is found. This will occur when the depth limit reaches D, the depth of the shallowest goal node. The algorithm is shown in figure 3.18. Iterative deepening combines the benefits of depth-first and breadth-first search. Like depth-first search, its memory requirements are modest, O, BD, to be precise. Like breadth-first search, it is complete when the branching factor is finite and optimal when the path cost is a non-decreasing function of the depth of the node. Figure 3.19 shows 4 iterations of iterative deepening search on a binary search tree, where the solution is found on the 4th iteration. Iterative deepening search may seem wasteful because states are generated multiple times. It turns out this is not too costly. The reason is that in a search tree with the same, or nearly the same, branching factor at each level, most of the nodes are in the bottom level, so it does not matter much that the upper levels are generated multiple times. In an iterative deepening search, the nodes on the bottom level, depth D, are generated once, those on the section 3.4. Uninformed search strategies 89. Function iterative deepening search, problem, returns a solution, or failure for depth equals 0 to infinity do result leftward arrow depth limited search, problem, depth, if result equals cutoff then return result. Figure 3.18 The iterative deepening search algorithm, which repeatedly applies depth limited search with increasing limits. It terminates when a solution is found or if the depth limited search returns failure, meaning that no solution exists. Limit equals 3. Limit equals 2. Limit equals 1. Limit equals 0 AA. ABC 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 ABC. ABC D E F G. 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 ABC D E F G H I J K L M N O. ABC D E F G H I J K L M N O. ABC D E F G H I J K L M N O. ABC D E F G H I J K L M N O. ABC D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. A B C D E F G H I J K L M N O. Figure 3.194 Iterations of iterative deepening search on a binary tree. 90 Chapter 3. Solving problems by searching. Next to bottom level are generated twice, and so on, up to the children of the root, which are generated d times. So the total number of nodes generated in the worst cases n IDS equals d, b plus, d1, b2 plus plus, 1, bd, which gives a time complexity of O, bd, asymptotically the same as breadth first search. There is some extra cost for generating the upper levels multiple times, but it is not large. For example, if b equals 10 and d equals 5, the numbers are n IDS equals 50 plus 400 plus 3, 000 plus 20, 000 plus 100, 000 equals 123, 450. N BFS equals 10 plus 100 plus 1, 000 plus 10, 000 plus 100, 000 equals 111, 110. If you are really concerned about repeating the repetition, you can use a hybrid approach that runs breadth first search until almost all the available memory is consumed, and then runs iterative deepening from all the nodes in the frontier. In general, iterative deepening is the preferred uninformed search method when the search space is large and the depth of the solution is not known. Iterative deepening search is analogous to breadth first search in that it explores a complete layer of new nodes at each iteration before going on to the next layer. It would seem worthwhile to develop an iterative analog to uniform cost search, inheriting the latter algorithm's optimal ID guarantees while avoiding its memory requirements. The idea is to use increasing path cost limits instead of increasing depth limits. The resulting algorithm, called iterative lengthening search, is explored in exercise 3.17. It turns out, unfortunately, that iterative lengthening incurs substantial overhead compared to uniform cost search. 3.4.6 Bidirectional search. The idea behind bidirectional search is to run two simultaneous searches, one forward from the initial state and the other backward from the goal, hoping that the two searches meet in the middle. Figure 3.20. The motivation is that BD/2 plus BD/2 is much less than BD, or in the figure, the area of the two small circles is less than the area of one big circle centered on the start and reaching to the goal. Bidirectional search is implemented by replacing the goal test with a check to see whether the frontiers of the two searches intersect. If they do, a solution has been found. It is important to realize that the first such solution found may not be optimal. Even if the two searches are both breadth first, some additional search is required to make sure there isn't another shortcut across the gap. The check can be done when each node is generated or selected for expansion and, with a hash table, will take constant time. For example, if a problem has solution depth d equals 6, and each direction runs breadth first search one node at a time, then in the worst case the two searches meet when they have generated all of the nodes at depth 3. For b equals 10, this means a total of 2,220 node generations, compared with 1,111,110 for a standard breadth first search. Thus, the time complexity of bidirectional search using breadth first searches in both directions is O, BD/2. The space complexity is also O, BD/2. We can reduce this by roughly half if one of the two searches is done by iterative deepening, but at least one of the frontiers must be kept in memory so that the intersection check can be done. This space requirement is the most significant weakness of bidirectional search. Section 3.4. Uninformed search strategies 91. Goal start. Figure 3.20 A schematic view of a bidirectional search that is about to succeed when a branch from the start node meets a branch from the goal node. The reduction in time complexity makes bidirectional search attractive, but how do we predecessor search backward? This is not as easy as it sounds. Let the predecessors of a state X be all those states that have X as a successor. Bidirectional search requires a method for computing predecessors. When all the actions in the state space are reversible, the predecessors of X are just its successors. Other cases may require substantial ingenuity. Consider the question of what we mean by the goal in searching backward from the goal. For the 8 puzzle and for finding a route in Romania, there is just one goal state, so the backward search is very much like the forward search. If there are several explicitly listed goal states, for example, the two dirt-free goal states in figure 3.3, then we can construct a new dummy goal state whose immediate predecessors are all the actual goal states. But if the goal is an abstract description, such as the goal that no queen attacks another queen in the n queens problem, then bidirectional search is difficult to use. 3.4.7 Comparing uninformed search strategies. Figure 3.21 compares search strategies in terms of the 4 evaluation criteria set forth in section 3.3.2. This comparison is for tree search versions. For graph searches, the main differences are that depth first search is complete for finite state spaces and that the space and time complexities are bounded by the size of the state space. Criterion breadth uniform depth iterative bidirectional first cost first limited deepening, if applicable. Complete. Yes a yes a b no no yes a d time O, bd, O, b1 plus c slash, O, bm, O, b, O, bd, O, bd/2, space O, bd, O, b1 plus c slash, O, bm, O, b, O, bd, O, bd/2, optimal. Yes yes no no yes yes d. Figure 3.21 Evaluation of tree search strategies. B is the branching factor, D is the depth of the shallowest solution, M is the maximum depth of the search tree, L is the depth limit. Superscript caveats are as follows: A complete if B is finite, B complete if step costs greater than or equal to 4 positive, C optimal if step costs are all identical, D if both directions use breadth first search. 92 Chapter 3. Solving problems by searching. 3.5 Informed, heuristic, search strategies. Informed search. This section shows how an informed search strategy, one that uses problem-specific knowledge beyond the definition of the problem itself, can find solutions more efficiently than can an uninformed strategy. Best first search. The general approach we consider is called best first search. Best first search is an instance of the general tree search or graph search algorithm in which a node is selected for expansion based on an evaluation function, f, n. The evaluation function is evaluation function construed as a cost estimate, so the node with the lowest evaluation is expanded first. The implementation of best first graph search is identical to that for uniform cost search, figure 3.14, except for the use of f instead of g to order the priority queue. The choice of f determines the search strategy. For example, as exercise 3.21 shows, best first tree search includes depth first search as a special case. Most best first algorithms include as a component of f a heuristic function, denoted h, and heuristic function h, n, equals estimated cost of the cheapest path from the state at node n to a goal state. Notice that h, n, takes a node as input, but, unlike g, n, it depends only on the state at that node. For example, in Romania, one might estimate the cost of the cheapest path from Arad to Bucharest via the straight line distance from Arad to Bucharest. Heuristic functions are the most common form in which additional knowledge of the problem is imparted to the search algorithm. We study heuristics in more depth in section 3.6. For now, we consider them to be arbitrary, non-negative, problem-specific functions, with one constraint: if n is a goal node, then h, n, equals 0. The remainder of the section covers two ways to use heuristic information to guide search. 3.5.1 Greedy Best First Search. Greedy Best First Search A tries to expand the node that is closest to the goal, on the grounds Greedy Best First Search that this is likely to lead to a solution quickly. Thus, it evaluates nodes by using just the heuristic function, that is, f, n, equals h, n. Let us see how this works for route finding problems in Romania. We use the straight line distance heuristic, which we will call HSLD. If the goal is Bucharest, we need to straight line distance know the straight line distances to Bucharest, which are shown in figure 3.22. For example, HSLD, in, Arad, equals 366. Notice that the values of HSLD cannot be computed from the problem description itself. Moreover, it takes a certain amount of experience to know that HSLD is correlated with actual road distances and is, therefore, a useful heuristic. Figure 3.23 shows the progress of a greedy best first search using HSLD to find a path from Arad to Bucharest. The first node to be expanded from Arad will be Sibiu because it is closer to Bucharest than either Zarind or Timișoara. The next node to be expanded will be Făgăraș because it is closest. Făgăraș in turn generates Bucharest, which is the goal. For this particular problem, greedy best first search using HSLD finds a solution without ever. 8. Our first edition called this greedy search, other authors have called it best first search. Our more general usage of the latter term follows Pearl, 1984. Section 3.5. Informed, heuristic, search strategies 93. Erdicini. Neam Oradia. Zarind. Timișoara. Mahadaya. Sibiu. Vitesti Râmnicu-Vâlcea. Vaslui. Bucharest. Georgia Hirsova. Efori. Arad. Lăgașe. Drobeta Craiova. Făgăraș. Iași. 0 160 242 161. 77 151. 366. 244 226. 176. 241. 253 329 80 199. 380 234. 374. 100 193. Figure 3.22 values of HSLD straight line distances to Bucharest. Expanding a node that is not on the solution path, hence, its search cost is minimal. It is not optimal, however, the path via Sibiu and Făgăraș to Bucharest is 32 kilometers longer than the path through Râmnicu-Vâlcea and Vitesti. This shows why the algorithm is called greedy. At each step it tries to get as close to the goal as it can. Greedy best first tree search is also incomplete even in a finite state space, much like depth first search. Consider the problem of getting from Iași to Făgăraș. The heuristic suggests that Neam be expanded first because it is closest to Făgăraș, but it is a dead end. The solution is to go first to Vaslui, a step that is actually farther from the goal according to the heuristic, and then to continue to Erdicini, Bucharest, and Făgăraș. The algorithm will never find a solution, however, because expanding Neam puts Iași back into the frontier. Iași is closer to Făgăraș than Vaslui is, and so Iași will be expanded again, leading to an infinite loop. The graph search version is complete in finite spaces, but not in infinite ones. The worst case time and space complexity for the tree version is O, BM, where M is the maximum depth of the search space. With a good heuristic function, however, the complexity can be reduced substantially. The amount of the reduction depends on the particular problem and on the quality of the heuristic. 3.5.2 A asterisk search, minimizing the total estimated solution cost. The most widely known form of best first search is called AA search, pronounced A star search search. It evaluates nodes by combining G, N, the cost to reach the node, and H, N, the cost to get from the node to the goal. F, N, equals G, N, plus H, N. Since G, N, gives the path cost from the start node to node N, and H, N, is the estimated cost of the cheapest path from N to the goal, we have F, N, equals estimated cost of the cheapest solution through N. Thus, if we are trying to find the cheapest solution, a reasonable thing to try first is the node with the lowest value of G, N, plus H, N. It turns out that this strategy is more than just reasonable, provided that the heuristic function H, N, satisfies certain conditions. A search is both complete and optimal. The algorithm is identical to uniform cost search except that A uses G plus H instead of G. 94 Chapter 3. Solving problems by searching. Râmnicu-Vâlcea. Zarind. Arad. Sibiu. Arad Făgăraș Oradea. Timișoara. Sibiu Bucharest. 329 374. 366 380 193. 253 0. Râmnicu-Vâlcea. Arad. Sibiu. Arad Făgăraș Oradea. Timișoara 329 Zarind 374. 366 176 380 193. Zarind. Arad. Sibiu Timișoara 253 329 374. Arad 366. A. The initial state. B. After expanding Arad. C. After expanding Sibiu. D. After expanding Făgăraș. Figure 3.23 stages in a greedy best first tree search for Bucharest with the straight line distance heuristic HSLD. Nodes are labeled with their H values. Conditions for optimality, admissibility and consistency. The first condition we require for optimality is that H, N, be an admissible heuristic. An admissible heuristic is one that never overestimates the cost to reach the goal. Because g, n, is the actual cost to reach n along the current path, and f, n, equals g, n, plus h, n, we have as an immediate consequence that f, n, never overestimates the true cost of a solution along the current path through n. Admissible heuristics are by nature optimistic because they think the cost of solving the problem is less than it actually is. An obvious example of an admissible heuristic is the straight line distance HSLD that we used in getting to Bucharest. Straight line distance is admissible because the shortest path between any 2 points is a straight line, so the straight. Section 3.5. Informed, heuristic, search strategies 95. Line cannot be an overestimate. In figure 3.24, we show the progress of an A-tree search for Bucharest. The values of G are computed from the step costs in figure 3.2, and the values of HSLD are given in figure 3.22. Notice in particular that Bucharest first appears on the frontier at step E, but it is not selected for expansion because its F cost, 450, is higher than that of Pătesti, 417. Another way to say this is that there might be a solution through Pătesti whose cost is as low as 417, so the algorithm will not settle for a solution that costs 450. Consistency is second, slightly stronger condition called consistency, or sometimes monotonicity. Monotonicity is required only for applications of A to graph search. 9 A heuristic H, n, is consistent if, for every node n and every successor n of n generated by any action A, the estimated cost of reaching the goal from n is no greater than the step cost of getting to n plus the estimated cost of reaching the goal from n. H, n, less than or equal to C, n, A, n, plus H, n. This is a form of the general triangle inequality, which stipulates that each side of a triangle inequality cannot be longer than the sum of the other two sides. Here, the triangle is formed by n, n, and the goal Gn closest to n. For an admissible heuristic, the inequality makes perfect sense. If there were a route from n to Gn via n that was cheaper than H, n, that would violate the property that H, n, is a lower bound on the cost to reach Gn. It is fairly easy to show, exercise 3.29, that every consistent heuristic is also admissible. Consistency is therefore a stricter requirement than admissibility, but one has to work quite hard to concoct heuristics that are admissible but not consistent. All the admissible heuristics we discuss in this chapter are also consistent. Consider, for example, HSLD. We know that the general triangle inequality is satisfied when each side is measured by the straight line distance and that the straight line distance between n and n is no greater than C, n, A, n. Hence, HSLD is a consistent heuristic. Optimality of A asterisk. As we mentioned earlier, A has the following properties. The tree search version of A is optimal if H, n, is admissible, while the graph search version is optimal if H, n, is consistent. We show the second of these two claims since it is more useful. The argument essentially mirrors the argument for the optimality of uniform cost search, with G replaced by F just as in the A algorithm itself. The first step is to establish the following: if H, n, is consistent, then the values of F, n, along any path are non-decreasing. The proof follows directly from the definition of consistency. Suppose n is a successor of n, then G, n, equals G, n, plus C, n, A, n, for some action A, and we have F, n, equals G, n, plus H, n, equals G, n, plus C, n, A, n, plus H, n, greater than or equal to G, n, plus H, n, equals F, n. The next step is to prove that whenever A selects a node n for expansion, the optimal path to that node has been found. Were this not the case, there would have to be another frontier node n on the optimal path from the start node to n, by the graph separation property of 9. With an admissible but inconsistent heuristic, A requires some extra bookkeeping to ensure optimality. 96 Chapter 3. Solving problems by searching. A. The initial state. B. After expanding Arad. C. After expanding Sibiu. Arad Sibiu Timishwara 447 equals 118 plus 329 Zerine 393 equals 140 plus 253 449 equals 75 plus 374. Arad 366 equals 0 plus 366. D. After expanding Rybnikov-Ilsa. E. After expanding Fagaras. F. After expanding Pătesti. Zerine Arad Sibiu Arad Timishwara Fagaras Oradia Rybnikov-Ilsa 447 equals 118 plus 329 449 equals 75 plus 374 646 equals 280 plus 366 413 equals 220 plus 193 415 equals 239 plus 176 671 equals 291 plus 380. Zerine Arad Sibiu Timishwara 447 equals 118 plus 329 449 equals 75 plus 374 Rybnikov-Ilsa Craiova Pătesti Sibiu 526 equals 366 plus 165 53 equals 300 plus 253 417 equals 317 plus 100. Zerine Arad Sibiu Arad Timishwara. Sibiu Bucharest Fagaras Oradia Craiova Pătesti Sibiu. 447 equals 118 plus 329 449 equals 75 plus 374 646 equals 280 plus 366 591 equals 338 plus 253 450 equals 450 plus 0526 equals 366 plus 164 17 equals 317 plus 100 553 equals 300 plus 253 671 equals 291 plus 380. Zerine Arad Sibiu Arad Timishwara. Sibiu Bucharest Oradia Craiova Pătesti Sibiu Bucharest Craiova Rybnikov-Ilsa 418 equals 418 plus 0. 447 equals 118 plus 329 449 equals 75 plus 374 646 equals 280 plus 366 591 equals 338 plus 253 450 equals 450 plus 0526 equals 366 plus 165 53 equals 300 plus 253 615 equals 455 plus 166 07 equals 414 plus 193. 671 equals 291 plus 380. Rybnikov-Ilsa. Fagaras Rybnikov-Ilsa. Arad Fagaras Oradia 646 equals 280 plus 366 415 equals 239 plus 176 671 equals 291 plus 380. Figure 3.24 stages in an A search for Bucharest. Nodes are labeled with F equals G plus H. The H values are the straight line distances to Bucharest taken from figure 3.22. Section 3.5. Informed, heuristic, search strategies 97. O. Z. A. T. L. M. DC. R. F. B. G. BUH. E. V. I. N. 380. 400. 420. S. Figure 3.25 map of Romania showing contours at f equals 380, f equals 400, and f equals 420, with Arad as the start state. Nodes inside a given contour have f costs less than or equal to the contour value. Figure 3.9, because f is non-decreasing along any path, n would have lower f cost than n and would have been selected first. From the two preceding observations, it follows that the sequence of nodes expanded by A using graph search is in non-decreasing order of f, n. Hence, the first goal node selected for expansion must be an optimal solution because f is the true cost for goal nodes, which have h equals 0, and all later goal nodes will be at least as expensive. The fact that f costs are non-decreasing along any path also means that we can draw contours in the state space, just like the contours in a topographic map. Figure 3.25 shows an example. Inside the contour labeled 400, all nodes have f, n, less than or equal to 400, and so on. Then, because A expands the frontier node of lowest f cost, we can see that an A search fans out from the start node, adding nodes in concentric bands of increasing f cost. With uniform cost search, A search using h, n, equals 0, the bands will be circular around the start state. With more accurate heuristics, the bands will stretch toward the goal state and become more narrowly focused around the optimal path. If C is the cost of the optimal solution path, then we can say the following. A expands all nodes with f, n. Completeness requires that there be only finitely many nodes with cost less than or equal to C, a condition that is true if all step costs exceed some finite and if B is finite. Notice that A expands no nodes with f, n, C for example, Timișoara is not expanded in figure 3.24 even though it is a child of the root. We say that the subtree below. 98 Chapter 3. Solving problems by searching. Pruning Timișoara is pruned, because HSLD is admissible, the algorithm can safely ignore the subtree while still guaranteeing optimality. The concept of pruning eliminating possibilities from consideration without having to examine them is important for many areas of AI. One final observation is that among optimal algorithms of this type, algorithms that extend search paths from the root and use the same heuristic information A is optimally efficient for any given consistent heuristic. That is, no other optimal algorithm is guaranteed optimally efficient to expand fewer nodes than A, except possibly through tie-breaking among nodes with f, n, equals C. This is because any algorithm that does not expand all nodes with f, n, needs. The catch is that, for most problems, the number of states within the goal contour search space is still exponential in the length of the solution. The details of the analysis are beyond the scope of this book, but the basic results are as follows. For problems with constant step costs, the growth in runtime as a function of the optimal solution depth D is analyzed in absolute error terms of the absolute error or the relative error of the heuristic. The absolute error is relative error defined as delta HH, where H is the actual cost of getting from the root to the goal, and the relative error is defined as HH/H. The complexity results depend very strongly on the assumptions made about the state space. The simplest model studied is a state space that has a single goal and is essentially a tree with reversible actions. The A puzzle satisfies the first and third of these assumptions. In this case, the time complexity of A is exponential in the maximum absolute error, that is, O, B delta. For constant step costs, we can write this as O, B D, where D is the solution depth. For almost all heuristics in practical use, the absolute error is at least proportional to the path cost H, so is constant or growing and the time complexity is exponential in D. We can also see the effect of a more accurate heuristic, O, B D, equals O, B, D, so the effective branching factor, defined more formally in the next section, is B. When the state space has many goal states, particularly near optimal goal states, the search process can be led astray from the optimal path and there is an extra cost proportional to the number of goals whose cost is within a factor of the optimal cost. Finally, in the general case of a graph, the situation is even worse. There can be exponentially many states with f, n. Design heuristics that are more accurate but not strictly admissible. In any case, the use of a good heuristic still provides enormous savings compared to the use of an uninformed search. In section 3.6, we look at the question of designing good heuristics. Computation time is not, however, A's main drawback. Because it keeps all generated nodes in memory, as do all graph search algorithms, A usually runs out of space long. Section 3.5. Informed, heuristic, search strategies 99. Function recursive best first search, problem, returns a solution, or failure return RBFS, problem, make node, problem.initial state, infinity. Function RBFS, problem, node f limit, returns a solution, or failure, and a new f cost limit if problem.goal test, node.state, then return solution, node, successors leftward arrow for each action in problem.actions, node.state, do add child node, problem, node, action, into successors if successors is empty then return failure, infinity for each s in successors do / asterisk update f with value from previous search, if any asterisk slash. S.f leftward arrow max, S.g plus S.h, node.f, loop do best leftward arrow the lowest f value node in successors if best.f limit then return failure, best.f alternative leftward arrow the second lowest f value among successors result, best.f leftward arrow RBFS, problem, best, min, f limit, alternative, if result equals failure then return result. Figure 3.26 the algorithm for recursive best first search. Before it runs out of time. For this reason, A is not practical for many large-scale problems. There are, however, algorithms that overcome the space problem without sacrificing optimality or completeness, at a small cost in execution time. We discuss these next. 3.5.3 Memory-bounded heuristic search. The simplest way to reduce memory requirements for A is to adapt the idea of iterative deepening to the heuristic search context, resulting in the iterative deepening A, IDA, alliterative deepening algorithm. The main difference between IDA and standard iterative deepening is that the cutoff used is the f cost, G plus H, rather than the depth. At each iteration, the cutoff value is the smallest f cost of any node that exceeded the cutoff on the previous iteration. IDA is practical for many problems with unit step costs and avoids the substantial overhead associated with keeping a sorted queue of nodes. Unfortunately, it suffers from the same difficulties with real valued costs as does the iterative version of uniform cost search described in exercise 3.17. This section briefly examines two other memory-bounded algorithms called RBFS and MA. Recursive best first search, RBFS, is a simple recursive algorithm that attempts to recursive best first search. Mimic the operation of standard best first search, but using only linear space. The algorithm is shown in figure 3.26. Its structure is similar to that of a recursive depth-first search, but rather than continuing indefinitely down the current path, it uses the f-limit variable to keep track of the f-value of the best alternative path available from any ancestor of the current node. If the current node exceeds this limit, the recursion unwinds back to the alternative path. As the recursion unwinds, our BFS replaces the f-value of each node along the path. Backed up value with a backed up value the best f-value of its children. In this way, our BFS remembers the f-value of the best leaf in the forgotten subtree and can therefore decide whether it's worth 100. Chapter 3. Solving problems by searching. Zerind Arad Sibu Arad Fagras Oradia Craiova Sibu Bucharest Craiova Rimna Kovilsa. Zerind Arad Sibu Bucharest Oradia Rimna Kovilsa. Zerind Arad Sibu Arad. Timishwara. Timishwara. Timishwara Fagras Oradia Rimna Kovilsa Craiova Patesti Sibu 646 415 671 526 553. 646 671 591 450. 646 671 526 553 418 615 607. 447 449. 447. 447 449. 449. 366 393. 366 393. 413. 415 413 417. 366 393 415 450 417 Rimna Kovilsa. Fagras. 447 415. 447. 447 417. A. After expanding Arad, Sibu, and Rimna Kovilsa. C. After switching back to Rimna Kovilsa and expanding Patesti. B. After unwinding back to Sibu and expanding Fagras. 447 447. Infinity. 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 417. 417. Patesti. Figure 3.27 stages in an RBFS search for the shortest route to Bucharest. The f-limit value for each recursive call is shown on top of each current node, and every node is labeled with its f-cost. A. The path via Rimna Kovilsa is followed until the current best leaf, Patesti, has a value that is worse than the best alternative path, Fagras. B. The recursion unwinds and the best leaf value of the forgotten subtree, 417, is backed up to Rimna Kovilsa, then Fagras is expanded, revealing a best leaf value of 450. C. The recursion unwinds and the best leaf value of the forgotten subtree, 450, is backed up to Fagras, then Rimna Kovilsa is expanded. This time, because the best alternative path, through Timishwara, costs at least 447, the expansion continues to Bucharest. Re-expanding the subtree at some later time. Figure 3.27 shows how RBFS reaches Bucharest. RBFS is somewhat more efficient than IDA, but still suffers from excessive node regeneration. In the example in Figure 3.27, RBFS follows the path via Rimna Kovilsa, then. Section 3.5. Informed, heuristic, search strategies 101. Changes its mind and tries Fagras, and then changes its mind back again. These mind changes occur because every time the current best path is extended, its f-value is likely to increase. H is usually less optimistic for nodes closer to the goal. When this happens, the second best path might become the best path, so the search has to backtrack to follow it. Each mind change corresponds to an iteration of IDA and could require many re-expansions of forgotten nodes to recreate the best path and extended one more node. Like a tree search, RBFS is an optimal algorithm if the heuristic function h, n, is admissible. Its space complexity is linear in the depth of the deepest optimal solution, but its time complexity is rather difficult to characterize. It depends both on the accuracy of the heuristic function and on how often the best path changes as nodes are expanded. IDA and RBFS suffer from using too little memory. Between iterations, IDA retains only a single number, the current f-cost limit. RBFS retains more information in memory. But it uses only linear space. Even if more memory were available, RBFS has no way to make use of it. Because they forget most of what they have done, both algorithms may end up re-expanding the same states many times over. Furthermore, they suffer the potentially exponential increase in complexity associated with redundant paths in graphs. See section 3.3. It seems sensible, therefore, to use all available memory. Two algorithms that do this are MA, memory bounded A, and SMA, simplified MA. SMA MA asterisk is well simpler, so SMA asterisk we will describe it. SMA proceeds just like A, expanding the best leaf until memory is full. At this point, it cannot add a new node to the search tree without dropping an old one. SMA always drops the worst leaf node, the one with the highest f-value. Like RBFS, SMA then backs up the value of the forgotten node to its parent. In this way, the ancestor of A forgotten subtree knows the quality of the best path in that subtree. With this information, SMA regenerates the subtree only when all other paths have been shown to look worse than the path it has forgotten. Another way of saying this is that, if all the descendants of a node n are forgotten, then we will not know which way to go from n, but we will still have an idea of how worthwhile it is to go anywhere from n. The complete algorithm is too complicated to reproduce here 10, but there is one subtlety worth mentioning. We said that SMA expands the best leaf and deletes the worst leaf. What if all the leaf nodes have the same f-value? To avoid selecting the same node for deletion and expansion, SMA expands the newest best leaf and deletes the oldest worst leaf. These coincide when there is only one leaf, but in that case, the current search tree must be a single path from root to leaf that fills all of memory. If the leaf is not a goal node, then even if it is on an optimal solution path, that solution is not reachable with the available memory. Therefore, the node can be discarded exactly as if it had no successors. SMA is complete if there is any reachable solution, that is, if the depth of the shallowest goal node is less than the memory size, expressed in nodes. It is optimal if any optimal solution is reachable, otherwise, it returns the best reachable solution. In practical terms, SMA is a fairly robust choice for finding optimal solutions, particularly when the state space is a graph, step costs are not uniform, and node generation is expensive compared to the overhead of maintaining the frontier and the explored set. 10. A rough sketch appeared in the first edition of this book. 102. Chapter 3. Solving problems by searching. On very hard problems, however, it will often be the case that SMA is forced to switch back and forth continually among many candidate solution paths, only a small subset of which thrashing can fit in memory. This resembles the problem of thrashing in disk paging systems. Then the extra time required for repeated regeneration of the same nodes means that problems that would be practically solvable by a given unlimited memory become intractable for SMA. That is to say, memory limitations can make a problem intractable from the point of view of computation time. Although no current theory explains the trade-off between time and memory, it seems that this is an inescapable problem. The only way out is to drop the optimal ID requirement. 3.5.4 Learning to search better. We have presented several fixed strategies: breadth first, greedy best first, and so on, that have been designed by computer scientists. Could an agent learn how to search better? The answer is yes, and the method rests on an important concept called the meta-level state space. Meta-level state space: each state in a meta-level state space captures the internal, computational, state of a program that is searching in an object-level state space such as Romania. For example, the internal object-level state space state of the A algorithm consists of the current search tree. Each action in the meta-level state space is a computation step that alters the internal state. For example, each computation step in A expands a leaf node and adds its successors to the tree. Thus, figure 3.24, which shows a sequence of larger and larger search trees, can be seen as depicting a path in the meta-level state space where each state on the path is an object-level search tree. Now, the path in figure 3.24 has 5 steps, including one step, the expansion of Pythagoras. That is not especially helpful. For harder problems, there will be many such missteps, and a meta-level learning algorithm can learn from these experiences to avoid exploring unpromised meta-level learning subtrees. The techniques used for this kind of learning are described in Chapter 21. The goal of learning is to minimize the total cost of problem solving, trading off computational expense and path cost. 3.6 Heuristic functions. In this section, we look at heuristics for the 8 puzzle, in order to shed light on the nature of heuristics in general. The 8 puzzle was one of the earliest heuristic search problems. As mentioned in section 3.2, the object of the puzzle is to slide the tiles horizontally or vertically into the empty space until the configuration matches the goal configuration, figure 3.28. The average solution cost for a randomly generated 8 puzzle instance is about 22 steps. The branching factor is about 3. When the empty tile is in the middle, 4 moves are possible; when it is in a corner, 2, and when it is along an edge, 3. This means that an exhaustive tree search to depth 22 would look at about 322 3.1 times 1010 states. A graph search would cut this down by a factor of about 170,000 because only 9/2 equals 181, 440 distinct states are reachable. See exercise 3.4. This is a manageable number, but. Section 3.6. Heuristic functions 103. 2. Start state goal state. 1. 3 4. 6 7. 5. 1. 2. 3. 4. 6. 7. 8. 5. 8. Figure 3.28 a typical instance of the 8 puzzle. The solution is 26 steps long. The corresponding number for the 15 puzzle is roughly 1013, so the next order of business is to find a good heuristic function. If we want to find the shortest solutions by using A, we need a heuristic function that never overestimates the number of steps to the goal. There is a long history of such heuristics for the 15 puzzle. Here are 2 commonly used candidates. H1 equals the number of misplaced tiles. For figure 3.28, all of the 8 tiles are out of position, so the start state would have H1 equals 8. H1 is an admissible heuristic because it is clear that any tile that is out of place must be moved at least once. H2 equals the sum of the distances of the tiles from their goal positions. Because tiles cannot move along diagonals, the distance we will count is the sum of the horizontal and vertical distances. This is sometimes called the city block distance or Manhattan distance. H2 is also admissible because all any move can do is move one tile one step Manhattan distance closer to the goal. Tiles 1 to 8 in the start state give a Manhattan distance of H2 equals 3 plus 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 2 equals 18. As expected, neither of these overestimates the true solution cost, which is 26. 3.6.1 The effect of heuristic accuracy on performance. One way to characterize the quality of a heuristic is the effective branching factor B. If the effective branching factor total number of nodes generated by A for a particular problem is n and the solution depth is d, then B is the branching factor that a uniform tree of depth d would have to have in order to contain n plus 1 nodes. Thus, n plus 1 equals 1 plus b, 2 plus b, d. For example, if A finds a solution at depth 5 using 52 nodes, then the effective branching factor is 1.92. The effective branching factor can vary across problem instances, but usually it is fairly constant for sufficiently hard problems. The existence of an effective branching factor follows from the result, mentioned earlier, that the number of nodes expanded by A grows exponentially with solution depth. Therefore, experimental measurements of B on a small set of problems can provide a good guide to the heuristic's overall usefulness. A well-designed heuristic would have a value of B close to 1, allowing fairly large problems to be solved at reasonable computational cost. 104 Chapter 3. Solving problems by searching. To test the heuristic functions H1 and H2, we generated 1,200 random problems with solution lengths from 2 to 24, 100 for each even number, and solved them with iterative deepening search and with A-tree search using both H1 and H2. Figure 3.29 gives the average number of nodes generated by each strategy and the effective branching factor. The results suggest that H2 is better than H1, and is far better than using iterative deepening search. Even for small problems with D equals 12, A with H2 is 50,000 times more efficient than uninformed. Iterative deepening search. Search cost, nodes generated, effective branching factor. DIDSA, H1, A, H2, IDSA, H1, A, H2. 2.10.662.45 1.79 1.79 for 112 13 12 2.87 1.48 1.45 6 680 20 18 2.73 1.34 1.308 6384 39 25 2.80 1.33 1.24 10 47,127 93 39 2.79 1.38 1.22 12 364 4035 227 73 2.78 1.42 1.24 14 to 539 113 to 1.44 1.23 16 to 1301 211 to 1.45 1.25 18 to 3056 363 to 1.4 1.46, 1.26, 20 to 7,276, 676 to 1.47, 1.27, 22 to 18,094, 1,219 to 1.48, 1.28, 24 to 39,135, 1,641 to 1.48, 1.26. Figure 3.29 Comparison of the search costs and effective branching factors for the iterative deepening search NA algorithms with H1, H2. Data are averaged over 100 instances of the A puzzle for each of various solution lengths D. One might ask whether H2 is always better than H1. The answer is essentially, yes. It is easy to see from the definitions of the two heuristics that, for any node n, H2, n, greater than or equal to H1, n. We thus say that H2 dominates H1. Domination translates directly into efficiency, A domination using. H2 will never expand more nodes than A using H1, except possibly for some nodes with F, n, equals C. The argument is simple. Recall the observation on page 97 that every node with F, n nodes, every node that is surely expanded by a search with H2 will also surely be expanded with H1, and H1 might cause other nodes to be expanded as well. Hence, it is generally better to use a heuristic function with higher values, provided it is consistent and that the computation time for the heuristic is not too long. 3.6.2 Generating admissible heuristics from relaxed problems. We have seen that both H1, misplaced tiles, and H2, Manhattan distance, are fairly good heuristics for the A puzzle and that H2 is better. How might one have come up with H2? Is it possible for a computer to invent such a heuristic mechanically? H1 and H2 are estimates of the remaining path length for the A puzzle, but they are also perfectly accurate path lengths for simplified versions of the puzzle. If the rules of the puzzle, section 3.6, heuristic functions 105, were changed so that a tile could move anywhere instead of just to the adjacent empty square, then H1 would give the exact number of steps in the shortest solution. Similarly, if a tile could move one square in any direction, even onto an occupied square, then H2 would give the exact number of steps in the shortest solution. A problem with fewer restrictions on the actions is relaxed problem called a relaxed problem. The state space graph of the relaxed problem is a supergraph of the original state space because the removal of restrictions creates added edges in the graph. Because the relaxed problem adds edges to the state space, any optimal solution in the original problem is, by definition, also a solution in the relaxed problem, but the relaxed problem may have better solutions if the added edges provide shortcuts. Hence, the cost of an optimal solution to a relaxed problem is an admissible heuristic for the original problem. Furthermore, because the derived heuristic is an exact cost for the relaxed problem, it must obey the triangle inequality and is therefore consistent. See page 95. If a problem definition is written down in a formal language, it is possible to construct relaxed problems automatically. Point 11 For example, if the A puzzle actions are described as a tile can move from square A to square B if A is horizontally or vertically adjacent to B and B is blank. We can generate three relaxed problems by removing one or both of the conditions. A tile can move from square A to square B if A is adjacent to B. B. A tile can move from square A to square B if B is blank. C. A tile can move from square A to square B. From A, we can derive H2, Manhattan distance. The reasoning is that H2 would be the proper score if we moved each tile in turn to its destination. The heuristic derived from B is discussed in exercise 3.31. From C, we can derive H1, misplaced tiles, because it would be the proper score if tiles could move to their intended destination in one step. Notice that it is crucial that the relaxed problems generated by this technique can be solved essentially without search, because the relaxed rules allow the problem to be decomposed into 8 independent subproblems. If the relaxed problem is hard to solve, then the values of the corresponding heuristic will be expensive to obtain. Point 12 A program called AppSolver can generate heuristics automatically from problem definitions, using the relaxed problem method and various other techniques. Previous, 1993. AppSolver generated a new heuristic for the A puzzle that was better than any pre-existing heuristic and found the first useful heuristic for the famous Rubik's Cube puzzle. One problem with generating new heuristic functions is that one often fails to get a single clearly best heuristic. If a collection of admissible heuristics H1, is available for a problem and none of them dominates any of the others, which should we choose? As it turns out, we need not make a choice. We can have the best of all worlds, by defining H, n, equals max H1, n, comma, n. 11 In chapters 8 and 10, we describe formal languages suitable for this task, with formal descriptions that can be manipulated. The construction of relaxed problems can be automated. For now, we use English. 12 Note that a perfect heuristic can be obtained simply by allowing H to run a full breadth first search on the sly. Thus, there is a trade-off between accuracy and computation time for heuristic functions. 106 Chapter 3. Solving problems by searching. Start state goal state. 1, 2, 3, 4, 6, 8, 5, 1, 2, 3, 6, 7, 8, 54. Figure 3.30 A subproblem of the A puzzle instance given in figure 3.28. The task is to get tiles 1, 2, 3, and 4 into their correct positions, without worrying about what happens to the other tiles. This composite heuristic uses whichever function is most accurate on the node in question. Because the component heuristics are admissible, H is admissible, it is also easy to prove that H is consistent. Furthermore, H dominates all of its component heuristics. 3.6.3 Generating admissible heuristics from subproblems, pattern databases. Subproblem admissible heuristics can also be derived from the solution cost of a subproblem of a given problem. For example, figure 3.30 shows a subproblem of the A puzzle instance in figure 3.28. The subproblem involves getting tiles 1, 2, 3, 4 into their correct positions. Clearly, the cost of the optimal solution of the subproblem is a lower bound on the cost of the complete problem. It turns out to be more accurate than Manhattan distance in some cases. Pattern database. The idea behind pattern databases is to store these exact solution costs for every possible subproblem instance in our example, every possible configuration of the 4 tiles and the blank. The locations of the other 4 tiles are irrelevant for the purposes of solving the subproblem, but moves of those tiles do count toward the cost. Then we compute an admissible heuristic HDB for each complete state encountered during a search simply by looking up the corresponding subproblem configuration in the database. The database itself is constructed by searching back 13 from the goal and recording the cost of each new pattern encountered. The expense of the search is amortized over many subsequent problem instances. The choice of 1-2-3-4 is fairly arbitrary. We could also construct databases for 5-6-7-8, for 2-4-6-8, and so on. Each database yields an admissible heuristic, and these heuristics can be combined, as explained earlier, by taking the maximum value. A combined heuristic of this kind is much more accurate than the Manhattan distance. The number of nodes generated when solving random 15 puzzles can be reduced by a factor of 1000. One might wonder whether the heuristics obtained from the 1-2-3-4 database and the 5-6-7-8 could be added, since the two subproblems seem not to overlap. Would this still give an admissible heuristic? The answer is no, because the solutions of the 1-2-3-4 subproblem and the 5-6-7-8 subproblem for a given state will almost certainly share some moves. It is 13. By working backward from the goal, the exact solution cost of every instance encountered is immediately available. This is an example of dynamic programming, which we discuss further in Chapter 17. Section 3.6. Heuristic functions 107. Unlikely that 1-2-3-4 can be moved into place without touching 5-6-7-8, and vice versa. But what if we don't count those moves? That is, we record not the total cost of solving the 1-2-3-4 subproblem, but just the number of moves involving 1-2-3-4. Then it is easy to see that the sum of the two costs is still a lower bound on the cost of solving the entire problem. This is the idea behind disjoint pattern databases. With such databases, it is possible to solve disjoint pattern databases random 15 puzzles in a few milliseconds. The number of nodes generated is reduced by a factor of 10,000 compared with the use of Manhattan distance. For 24 puzzles, a speedup of roughly a factor of 1,000,000 can be obtained. Disjoint pattern databases work for sliding tile puzzles because the problem can be divided up in such a way that each move affects only one subproblem because only one tile is moved at a time. For a problem such as Rubik's Cube, this kind of subdivision is difficult, because each move affects 8 or 9 of the 26 cubies. More general ways of defining additive. Admissible heuristics have been proposed that do apply to Rubik's Cube, Yang et al., 2008, but they have not yielded a heuristic better than the best non-additive heuristic for the problem. 3.6.4 Learning heuristics from experience. A heuristic function h, n, is supposed to estimate the cost of a solution beginning from the state at node n. How could an agent construct such a function? One solution was given in the preceding sections, namely, to devise relaxed problems for which an optimal solution can be found easily. Another solution is to learn from experience. Experience here means solving lots of 8 puzzles, for instance. Each optimal solution to an 8-puzzle problem provides examples from which h, n, can be learned. Each example consists of a state from the solution path and the actual cost of the solution from that point. From these examples, a learning algorithm can be used to construct a function h, n, that can, with luck, predict solution costs for other states that arise during search. Techniques for doing just this using neural nets, decision trees, and other methods are demonstrated in Chapter 18. The reinforcement learning methods described in Chapter 21 are also applicable. Feature inductive learning methods work best when supplied with features of a state that are relevant to predicting the state's value, rather than with just the raw state description. For example, the feature number of misplaced tiles might be helpful in predicting the actual distance of a state from the goal. Let's call this feature x1, n. We could take 100 randomly generated 8 puzzle configurations and gather statistics on their actual solution costs. We might find that when x1, n, is 5, the average solution cost is around 14, and so on. Given these data, the value of